On October 2nd, an exceptionally swift phenomenon streaked through the Martian atmosphere. Stephen Burns, an amateur astrophotographer, detected it within NASA's raw images captured by the Perseverance rover. He compiled a time-lapse sequence, compressing 9 minutes of data, which vividly illustrated the object's movement at 60 kilometers per second, contrary to the usual drift of stars. However, the situation escalated in strangeness. Other observers began examining the same imagery, reporting sightings of multiple objects, not just a solitary entity. These reports described several rapidly moving anomalies within the October 3rd data, accompanied by an inexplicable green luminescence. NASA had strategically scheduled this particular observation. Multiple Mars orbiters were intended to capture unprecedentedly close imagery of an interstellar visitor. The Mars Express spacecraft, equipped with a high-resolution camera capable of detailing features as small as 30 kilometers, alongside the ExoMars Trace Gas Orbiter, all directed their sensors towards object Oumuamua during its October 3rd close approach. Subsequently, a profound silence ensued, with no official images or data being released, leaving a void of information. Concurrently, Harvard's Avi Loeb published findings that have deeply unsettled the global astronomical community. It is now theorized that Oumuamua might have been the origin of the renowned 1977 WOW signal. The probability of this alignment occurring by mere chance is a mere 0.6%. Nevertheless, the connection to the WOW signal is merely the commencement of the enigma, as Oumuamua defies all established principles governing cometary behavior. It is observed to be expelling industrial-grade nickel alloys into space. Its tail is directed contrary to expectations. It exhibits a green hue when such coloration is scientifically unwarranted. Furthermore, its trajectory is so precisely aligned with Earth's orbital path that the statistical likelihood is astronomically improbable. Some have posited it as the largest interstellar object ever documented. Others have deemed it an impossibility. The scientific community is labeling it as potentially artificial. Currently, it is obscured by the sun, rendering it invisible to us, and is nearing its closest proximity to our star. The question remains, what will transpire when it re-emerges? Before delving deeper, if you find this narrative compelling, please engage the like button and subscribe to ensure you don't miss subsequent developments. Kindly share in the comments your listening location, the current time there, and whether you perceive one object or several. To aid in the growth of this community, please share this content on X, Facebook, Reddit, or your preferred messaging platform. We are immensely grateful for your consistent support. Chapter 1. An astonishing revelation. Multiple objects identified. Let us return to October 2nd. Stephen Burns was not anticipating any extraordinary discoveries. His objective was purely to process the raw image data that NASA makes accessible to the public, originating from the Perseverance rover. The rover had been programmed to scan the night sky during a specific temporal interval, coinciding with the predicted closest approach of Oumuamua to Mars. It is important to note that closest in this context refers to a separation of approximately 29 million kilometers. Burns meticulously captured 9 consecutive minutes of imagery, subsequently combining them into an animation. This technique, common in astrophotography, serves to accentuate motion imperceptible in a singular frame. While stars typically appear to traverse the frame due to Mars's rotation, this anomaly exhibited distinct behavior. An object was observed cutting across this stellar motion at an inexplicably unusual angle. The sheer velocity was the initial indicator. Traveling at 60 kilometers per second, Oumuamua surpasses the speed of nearly every object within our solar system. For perspective, Earth's orbital velocity around the Sun is approximately 30 kilometers per second. The Parker Solar Probe, humanity's fastest-moving spacecraft, achieves a peak speed of 192 kilometers per second, but only during its closest solar proximity. Oumuamua, however, maintains this astonishing pace throughout its transit. Burns disseminated his animation online. Within hours, fellow amateur astronomers initiated their own analyses. It was then that an individual identified by the username Nakataf, a German moniker translating to night monkey, put forth a claim that sent significant reverberations through the observational community. In the imagery from October 3rd, Nakataf asserted, "Multiple comets are visible, not one entity, but several." Another contributor, Alexander Fuhm, drew attention to a different peculiarity. "What is the flash at second 0003 indicated in green?" he inquired. A frame-by-frame review of Burns's animation reveals, at the 3-second mark, a fleeting greenish glow. This is not an artifact of the camera, nor is it a cosmic ray impact, which would manifest as a solitary bright pixel. Rather, it presents as a diffuse luminescence, localized yet distinct. Green light in the vacuum of space originates from specific phenomena. On Earth, we associate it with auroras, the combustion of copper, or certain bioluminescent organisms. In space, green emission typically arises from oxygen or from a molecular compound known as dicarbon, consisting of two bonded carbon atoms. Comets occasionally emit a green light when dicarbon within their comas is excited by solar radiation. However, a critical issue arises. Spectroscopic analysis of Oumuamua, conducted using the Very Large Telescope, revealed an almost complete absence of dicarbon. The object is, in astronomical parlance, depleted of this compound, and therefore should not be exhibiting a green luminescence. Despite this, photographic evidence from ground-based telescopes in early September clearly depicted a developing green hue surrounding the object. The green flash observed in the Martian imagery, if indeed authentic, adds another perplexing layer to this enigma. Regarding the reported multiple objects, this is where speculation takes root, albeit from individuals possessing telescopes and image processing software, rather than from unfounded conjecture. When the star field in Burns's animation is stabilized, accounting for Mars's rotation and the motion of the primary object, at least one or two additional points of light emerge, moving at differing velocities. Could these be imaging artifacts? Undeniably possible. Could they be background asteroids fortuitously situated within the frame? Plausible. Could they represent distinct fragments or even smaller companions accompanying Oumuamua? This is the unresolved question, as NASA has yet to release the pertinent data. The Mars Reconnaissance Orbiter's High-Resolution Imaging Science Experiment, HiRISE camera, observed Oumuamua on October 2nd, between the hours of 1 and 4 in the morning, Martian local time. The European Space Agency's Trace Gas Orbiter and Mars Express also acquired observations on October 3rd. These were not casual photographic moments, but rather precisely coordinated, pre-planned scientific endeavors aimed at obtaining the highest resolution data ever procured of an interstellar object. HiRISE, the High-Resolution Imaging Science Experiment, possesses the capability to resolve features as minute as 30 centimeters on Mars's surface from orbit. When directed at an object 29 million kilometers distant, it should still yield a resolution of approximately 30 kilometers per pixel. This implies that if Oumuamua possesses a nucleus measuring 5 kilometers across, as recent estimations suggest, It ought to appear as a luminous cluster of pixels within the high-rise imagery. More significantly, high-rise would be instrumental in discerning between a singular, cohesive nucleus and a fragmented or multi-component structure. Any unusual aspects of its composition or the presence of companion objects would be documented. Consequently, where are the images? NASA's official statements have been notably brief. The Mars orbiters successfully executed their observational protocols. The data is undergoing processing, and updates will be disseminated as analyses progress. This communication occurred over 24 hours ago. In the realm of space imaging, a 24-hour period is ample time to provide at least a preliminary review of raw data. Some observers have noted that the United States government has been experiencing various administrative challenges that have impacted the release of scientific data. However, the European Space Agency operates independently and should not be subject to such constraints. Yet, the imagery from ESA's missions has also not been made public. This reticence feels deliberate. When official channels fall silent, amateur observers naturally begin to converse. Because, to be certain, the Perseverance rover did capture something. Multiple amateur analysts, poring over the same publicly accessible raw data, are identifying anomalies. The object, or objects, displayed velocities consistent with Oumuamua. Additionally, there is the inexplicable green flash. What remains unknown is whether these perceived multiple objects are genuine, whether they are separate from the primary comet, and what NASA and ESA have observed with their vastly superior instruments. The October 3rd flyby represented the closest an interplanetary spacecraft has ever come to an active interstellar object. This was our pivotal opportunity to ascertain the true nature of Oumuamua, to examine its structure at close range, and to determine if its behavior aligns with that of a conventional comet or something entirely distinct. As we await resolutions, the object itself continues its cosmic journey. It is presently approaching the Sun, venturing deeper into the inner solar system, where Earth-based telescopes lose visibility due to the Sun's glare. By the latter part of October, it will be positioned directly behind our star from our vantage point, rendering it completely concealed. Upon its reappearance in November or December, it will either validate all naturalistic explanations or demonstrate behavior utterly unprecedented for comets. However, before it recedes from view, it is imperative to discuss the true objective of the Martian observations and why the timing of this informational blackout holds greater significance than might initially appear. Chapter 2. The Martian Blackout. There exists a discernible pattern in how space agencies manage sensitive observations. When routine phenomena are captured, the data typically becomes available within hours. Raw imagery populates public databases, and press releases are promptly prepared. Scientists frequently share their findings on social media. Conversely, when unexpected events occur, the period of silence extends considerably. The technical rationale offered for such delays centers on intricate data processing pipelines and the necessity for rigorous calibration. Mars orbiters do not transmit images instantaneously. They store acquired observations on board, subsequently transmitting them to Earth during designated communication intervals. From there, the data undergoes several processing stages, including geometric correction, radiometric calibration, and noise reduction. For standard surface observations, this entire procedure typically spans between 6 and 12 hours. For a celestial body in motion against the backdrop of stars, this duration may double. We are now well beyond 48 hours since the observations on October 3rd. However, another factor is at play, one that is seldom mentioned in official communications, but is well understood within the research community that relies heavily on NASA's data. Budgetary constraints and administrative disruptions have introduced bottlenecks into data release protocols. This is not a formal cessation of operations, but rather the bureaucratic friction that transforms routine procedures into protracted ones. Staff may be working reduced hours, priority systems might be reallocated, and review chains can become significantly longer. The European Space Agency operates under a different administrative framework, yet the imagery from its Mars Express and ExoMars Trace Gas Orbiter missions has also not been released. This suggests either a coordinated decision to withhold preliminary data until a comprehensive analysis is complete, or the presence of technical challenges that both agencies are simultaneously confronting. The question arises, what could be sufficiently challenging to precipitate such a delay? Consider the intended capabilities of these instruments. The color and stereo surface. Imaging system, CASES, aboard the Trace Gas Orbiter can resolve features as small as approximately 4.5 meters per pixel when imaging Mars. When directed towards an object 29 million kilometers away, its resolution diminishes considerably, though its sensitivity remains exceptionally high. It is designed to detect subtle variations in the coloration of Martian surface materials. If Oumuamua were emitting multiple types of ice, if its coma exhibited compositional heterogeneity, or if structurally distinct regions were present, CASES would undoubtedly capture such details. Mars Express carries the high-resolution stereo camera, which, despite its nomenclature, primarily focuses on three-dimensional topographical mapping. For a distant comet, its stereo capabilities are less critical than its ability to capture imagery across multiple wavelengths simultaneously. This camera can differentiate between dust, water ice, carbon dioxide ice, and various minerals by analyzing how they reflect different light spectrums. Furthermore, the Mars Reconnaissance Orbiter's HiRISE instrument, previously mentioned, possesses capabilities beyond mere image capture. It collects data across three distinct color bands: blue, green, red, and near-infrared. When directed at a comet, these bands reveal different aspects of its composition and activity. Blue and green light interact with gases within the coma, while red and near-infrared wavelengths can penetrate thin dust layers, exposing subsurface structures. If the comet were releasing material jets from specific points on its nucleus, if these jets possessed differing compositions, or if variations in brightness across the object suggested an uneven surface, HiRISE would meticulously document all such phenomena. And here's a crucial aspect of sensitive imagery. It sometimes reveals features that necessitate consultation before public release, not due to any conspiracy, but because preliminary observations can be easily misinterpreted without appropriate context. If HiRISE had captured something appearing unusual, mission scientists would prioritize ruling out instrumental anomalies, cosmic ray interference, or processing errors before disseminating the data. However, while we await the official channels to open, there is Simeon Schmaus. Schmaus is an astrophotographer renowned for his expertise in processing raw planetary data. He is recognized within the community for his proficiency in extracting signal from noisy imagery, stabilizing shaky video footage, and revealing subtle features that initial processing might overlook. On October 1st, one day prior to Stephen Burns's time-lapse capture on October 2nd, Perseverance acquired a series of night sky images. These were promptly uploaded to NASA's raw image database. As is standard practice for all Perseverance images, they became accessible within hours of their reception on Earth. Schmaus downloaded these images, applied his specialized processing techniques, and claimed to have detected an early indication of Oumuamua within those frames. This claim has not yet been independently corroborated, At such a distance and angle, the object would have been exceedingly faint. However, if verified, it would suggest that the comet was detectable even before the designated observation window. More intriguingly, Schmaus noted that the observed motion did not perfectly align with the predicted trajectory, exhibiting a slight deviation. He shared his findings on social media, emphasizing that further analysis was required, but deeming the preliminary results compelling. Subsequently, much like the official sources, he ceased public commentary. Whether he is still engaged in analysis, has uncovered information he wishes to confirm before public discussion, or has been requested to withhold his findings, remains unknown. What is evident is the existence of a void, a gap between what should be routine data disclosure and the current reality, a chasm between the scheduled observations and the data we are able to examine. This void is filled with amateur discoveries, unexplained green flashes, and assertions of multiple objects that neither official body can definitively confirm nor deny. The Perseverance rover continues its surface mission. Its cameras remain operational, and its data continues to be uploaded to the public database. However, the specific images from those critical nights, the ones of paramount importance, are currently undergoing scrutiny in silence. By October 29th, Oumuamua will reach perihelion, its closest point to the Sun. At this juncture, it will be positioned directly behind our star from Earth's perspective, rendering it invisible to both ground-based and space-based observatories. The window for observation is rapidly diminishing. Whatever information NASA and ESA have obtained, whatever Schmaus has discovered, whatever processes are unfolding behind the review stages and data pipelines, time is of the essence. Because if there is something extraordinary about this object, if those multiple points of light are real, if the green flash carries significant meaning, we must ascertain this before it vanishes into the solar glare. Should definitive answers elude us, we will be compelled to await its emergence on the opposing side in November, potentially altered by its close solar encounter and potentially exhibiting behaviors entirely alien to natural comets. However, there is another compelling reason for the significance of this timing. While our attention has been focused on the potential revelations from the Martian observations, Avi Loeb has been meticulously tracing Oumuamua's trajectory, not merely through our solar system, but backward through time. His findings establish a profound connection between this object and one of the most iconic unexplained signals in astronomical history. Chapter 3. The WOW Signal Revelation. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University was conducting a routine sky survey, searching for signals that might indicate the presence of technologically advanced civilizations beyond Earth. The telescope operated autonomously, scanning narrow bands of radio frequencies and logging intensity readings on continuous paper. Astronomer Jerry Amon, reviewing the printouts 3 days later, noticed something that prompted him to reach for a red pen. A signal had appeared, strong and narrow band, lasting precisely 72 seconds. Its intensity was so far above the background noise that Amon circled the alphanumeric sequence and scribbled a single word in the margin. Wow. The signal originated from the direction of Sagittarius, near the globular cluster M55. It was detected at a frequency of 1,420 megahertz, which falls within a protected radio astronomy band. Human transmissions are expressly forbidden at this frequency. The signal's bandwidth was narrow, less than 10 kilohertz, precisely what would be expected from an artificial transmitter rather than a natural astronomical source. The Big Ear telescope never detected the signal again. Subsequent observations yielded no results. For nearly 50 years, the WOW signal has remained one of astronomy's most profound mysteries. until Avi Loeb undertook the calculation of Oumuamua's position on that specific date. By extrapolating backward from the object's current trajectory and velocity, Loeb traced its path through space. In August of 1977, Oumuamua would have been situated approximately 600 astronomical units from Earth. This represents 600 times the distance between Earth and the Sun, placing it far within the outer reaches of the solar system, though not yet in true interstellar space. The WOW signal emanated from sky coordinates corresponding to a right ascension of 19 hours 25 minutes and a declination of -27 degrees. These coordinates point towards the constellation Sagittarius. Loeb calculated Oumuamua's position on August 15, 1977. The object would have been at a right ascension of 19 hours 21 minutes and a declination of -19 degrees, with a separation of 4 degrees in right ascension and 8 degrees in declination. In astronomical terms, this is remarkably close. The probability of two random directions in the sky aligning within 9 degrees of each other is approximately 0.6%. However, mere alignment does not establish causation. Loeb proceeded further. If Oumuamua were the source of the WOW signal, what would be the required power output of its transmitter? The signal intensity detected by Big Ear ranged from 54 to 212 Janskis. A Jansky is a unit used to measure radio flux density. For comparative purposes, the most powerful radio sources in the sky, such as the Sun or Jupiter, typically register in the hundreds to thousands of Janskis when observed at specific frequencies. At a distance of 600 astronomical units, generating the observed intensity would necessitate a transmitter outputting between 0.5 gigawatt and 2 gigawatts. This power range is comparable to that of a typical nuclear power reactor on Earth. While not inherently impossible, nor even particularly advanced for a civilization capable of interstellar travel, it is noteworthy because it represents the approximate power budget that would be logical for a deep space probe attempting communication across vast distances. There is an additional detail. The WOW signal exhibited a slight frequency shift. It was detected at 1420.4556 megahertz, which is approximately 10 kilohertz higher than the frequency of the neutral hydrogen line. This indicates a blue shift, signifying that the source was moving towards Earth. Oumuamua is approaching the Sun at a velocity of approximately 60 kilometers per second. When accounting for Earth's motion and geometric orientation in August of 1977, the relative velocity would indeed produce a blue shift. Loeb calculated the expected shift, finding it to be close to the observed value, though not an exact match. This discrepancy could be attributed to uncertainties in the precise positional and velocity vectors, or perhaps the signal was transmitted directionally rather than omnidirectionally. From a strategic perspective, this becomes particularly interesting. If an intelligence wished to announce its presence, broadcasting near the hydrogen line is a logical choice. Hydrogen is the most abundant element in the universe. The 21-centimeter hydrogen line is so fundamental to radio astronomy that any civilization possessing radio technology would undoubtedly monitor it. It serves as a universal cosmic calling card frequency. The WOW signal persisted for 72 seconds, a duration dictated by the operational mechanics of the Big Ear radio telescope. This instrument employed two distinct feed horns, spatially separated in the sky, which simultaneously surveyed adjacent celestial regions as Earth's rotation brought them into alignment with the target. Each individual feed horn possessed a scanning window of 36 seconds. The extraterrestrial signal was detected sequentially by both horns, consequently extending the observation period to the full 72 seconds. This observation implies that the source was either continuously transmitting or maintained its broadcast for the entire interval during which Big Ear was capable of detecting it. It was not an ephemeral pulse, but rather a sustained transmission. Should the object designated 3 Atlas be the originator, this scenario immediately presents several perplexing questions. Was this a beacon, signifying its presence to any potential listeners? Or perhaps a navigational signal intended to mark a position for another spacecraft? Alternatively, could it have been an attempt at communication, conveying information that we currently lack the sophistication to decipher? Then again, it might be entirely unconnected, a mere cosmic happenstance where an interstellar comet coincidentally aligned with an unidentified natural radio source. The fundamental issue is that we possess no radio telescope data pertaining to 3 Atlas. This is obviously true for August of 1977, but it also holds true for the present day. No astronomical observatory has reported directing its radio dishes towards this celestial body. The focus thus far has been predominantly on optical observations, spectroscopic analysis, and imaging. The inquiries have centered on its composition and structural characteristics, rather than its potential for transmission. Avi Loeb contends that this investigative approach requires immediate modification. The object is approaching its perihelion, drawing nearer to the sun. This proximity signifies elevated temperatures, increased activity, and consequently, more available energy should any form of technological system be involved. If it transmitted a signal from an astounding 600 astronomical units, and if it is engineered to communicate at specific junctures in its journey, then this current phase would be the opportune moment. Radio telescopes such as the Very Large Array situated in New Mexico, the successor facilities to Arecibo, and even the expansive arrays in China and Australia could meticulously monitor 3 Atlas across a broad spectrum of frequencies. This surveillance would extend beyond the mere hydrogen line to encompass the entire spectrum where artificial signals might conceivably manifest. The observational procedure would be relatively straightforward. Direct the instruments, listen intently, compare the received signals against the ambient background noise, and meticulously search for any narrow-band transmissions, any discernible modulation patterns, or any recurring structural elements that are uncharacteristic of natural cosmic phenomena. If nothing is detected, then so be it. The expenditure of a few hours of telescope time would suffice to invalidate this hypothesis. However, should something be found, if 3 Atlas is indeed emitting radio signals, even faint ones, or those that appear intermittently, this would fundamentally alter our interpretation of this object. This is because a comet, a mere aggregate of ice and rock, even one originating from another star system, does not generate radio signals at specific frequencies. While natural astronomical sources do produce radio emissions, these are typically broadband, chaotic, and devoid of the intricate structure that suggests deliberate intent. The WOW signal, in contrast, possessed structure. It exhibited a narrow bandwidth and appeared at a frequency of significant scientific interest. And if Avi Loeb's assessment regarding the alignment is accurate, if the calculated 0.6% coincidence actually represents causation, then somewhere within the distant reaches of our solar system, 48 years ago, an entity transmitted a signal powerful enough to be detected. That entity is now hurtling past Mars, concealed from our view by the sun, exhibiting behaviors entirely inconsistent with those expected of a comet. The pertinent question is not whether we ought to be listening, but rather why we have not already commenced doing so. Chapter 4. It is producing industrial alloys in space. As comets approach the sun, they commence shedding material from their outer surfaces. Ice transitions directly from a solid state to a gaseous one through sublimation. Dust particles are lifted away. Volatile compounds that were previously trapped are released. And occasionally, if a comet achieves a sufficient temperature, trace quantities of metals vaporize from the dust grains embedded within the ice. Nickel and iron are observed to appear together in these outgassing plumes. Their co-occurrence is consistent because they are formed together during stellar processes, are present together in meteoritic material, and sublimate at comparable temperatures. The precise ratio can vary slightly from one comet to another, but it adheres to a predictable pattern. For every atom of nickel detected, approximately 10 atoms of iron are expected. The preceding interstellar visitor, Comet 24/Borrelly, conformed to this rule flawlessly. Comets within our solar system also follow this pattern. Every icy body that has been observed to exhibit metallic emission adheres to this principle, with the sole exception of 3 Atlas. The European Very Large Telescope, situated in Chile, has been meticulously observing this object, utilizing its ultraviolet and visual spectrograph, an instrument engineered for the exceptionally precise dissection of light into its constituent wavelengths. Between the months of August and September, observers successfully captured spectroscopic data across 6 distinct temporal intervals as the comet traversed its trajectory from 3.14 astronomical units down to 2.14 astronomical units from the Sun. In every observational window, emission lines corresponding to nickel were conspicuously present in the spectrum, appearing bright, clear, and unequivocally identifiable. Iron, however, only became apparent when the comet drew nearer than 2.64 astronomical units. Prior to reaching this threshold, nickel was detected without any corresponding iron signature. Subsequent to this point, nickel was observed alongside some iron, but in ratios that deviated drastically from anything previously observed in other comets. The measured ratio of nickel to iron was orders of magnitude greater than the solar abundance ratios, significantly higher than typical cometary ratios, and far exceeding what natural geological processes would be expected to produce. The rate at which this material was being generated rendered the situation even more peculiar. 3 Atlas was expelling nickel gas at an approximate rate of 5 grams per second when it was initially observed. As the comet journeyed closer to the Sun and consequently warmed, this rate escalated dramatically. 5 grams per second might not sound substantial until one considers its implications. This equates to approximately 430 kilograms per day, or over 3 tons of nickel per week, emanating from an object theoretically composed primarily of water ice and rock. The surface temperature at 2.8 astronomical units, the location where a significant portion of this emission was observed, is far too low to facilitate the vaporization of silicate minerals or metallic grains that would contain nickel and iron. For the normal sublimation of refractory materials to occur, the comet would need to be at least twice as close to the Sun. This suggests that an alternative process is at play. The research team has posited several potential explanations. One possibility is that the nickel exists in a particularly volatile form. Nickel tetracarbonyl, a highly unstable compound, readily dissociates under ultraviolet radiation, releasing free nickel atoms into the coma. However, the formation of nickel tetracarbonyl necessitates specific chemical conditions, particular pathways that are not commonly encountered in natural processes. On Earth, nickel tetracarbonyl is produced industrially as part of the Mond process, employed for the purification of nickel from its ore. This involves heating impure nickel with carbon monoxide under precise temperature and pressure conditions, leading to the formation of gaseous nickel carbonyl. This compound is then subsequently decomposed at higher temperatures, resulting in the deposition of pure nickel. the observed chemical signature of 3 Atlas, releasing nickel without a corresponding presence of iron, closely mimics the output of this industrial refining procedure. Another possibility mentioned by the researchers is that the nickel is integrated within organic compounds or exists as nanoscale particles that exhibit a different response to solar heating compared to bulk metallic grains. Perhaps photon-stimulated desorption, a phenomenon where light directly dislodges atoms from a surface, is preferentially releasing nickel. While these represent plausible natural mechanisms, they are complex, requiring specific environmental conditions, and are dependent on the comet's formation history, its interstellar journey, and the radiation environment it has encountered. 3 Atlas likely originated in the thick disk of the Milky Way, a region characterized by older, metal-poor stars. Models suggest it spent between 4 and 7 billion years traversing interstellar space before entering our solar system. During this extensive voyage, it would have been subjected to cosmic rays, background radiation, and collisions with interstellar dust and gas. Could this prolonged exposure have engendered surface chemistry exotic enough to account for the observed nickel emissions? Is it conceivable that the comet accumulated material during its interstellar passage that, upon being heated by the sun, releases metals in anomalous ratios? One would anticipate comets formed around different stars to display distinct chemical compositions. Protostellar disks vary in their elemental makeup. The mixture of elements, the proportion of volatile to refractory materials, and the structural complexity of organic molecules all differ depending on the location and epoch of solar system formation. Nevertheless, the fundamental laws of physics remain constant. Nickel and iron continue to form together in supernovae, condense together in protostellar disks, and sublimate at similar temperatures. To achieve their separation and release in such dramatically different ratios would necessitate overcoming fundamental chemical relationships. This is unless the nickel is not originating from the sublimation of ice and rock, but rather is being released through a process involving chemistry that we do not typically associate with comets. Avi Loeb has predictably highlighted that the observations align with what one would expect from artificial nickel production. This is not to suggest the comet is a manufacturing facility, but rather that if it were a technological artifact with nickel-based components, or a surface coating rich in nickel accumulated during its interstellar travels, solar heating could ablate that material. The absence of iron would then simply reflect the composition of whatever material is being eroded. The counterargument to this proposition is straightforward. Why would an advanced civilization construct something from materials that ablate so readily? If one is designing an interstellar probe intended to endure for billions of years, the use of materials that begin to vaporize upon nearing a star would seem counterintuitive. This is unless the vaporization serves an intentional purpose, such as cooling, shedding mass to adjust trajectory, generating a signal, or creating a visible marker observable from a great distance. Alternatively, the coating accumulated during the journey might not have been part of the original design. Interstellar space is not an empty void. At speeds of 60 kilometers per second, even diffuse gas and dust particles impact with considerable energy. Over millions of years, a spacecraft would accumulate surface material, much like a comet does. If this accumulated material happened to be enriched in certain elements, depending on the galactic regions the object traversed, unusual compositions could be observed. The data obtained from the Very Large Telescope does not definitively prove any of these hypotheses. It merely establishes that 3 Atlas is exhibiting anomalous behavior. The presence of nickel without iron, the extreme rates of emission, and the timing of the appearance of different emissions do not align comfortably with our established models of cometary behavior. Furthermore, nickel represents only one facet of this enigma. While the Very Large Telescope was documenting metallic emissions, the Hubble Space Telescope was capturing images that revealed something even more fundamental, something that challenges the very definition of what constitutes a comet. Chapter 5. The Anti-Tail Anomaly. Comet tails invariably point away from the sun. This is one of the initial characteristics one learns about comets. Their tails are not indicative of their motion, but are instead propelled by solar radiation and the solar wind. Photons possess momentum. When billions of photons per second impact dust particles and ionized gas molecules, they transfer this momentum outward, thereby generating the characteristic tail that consistently streams away from the sun. The directionality of the tail is so fundamental to cometary behavior that upon observing a comet, astronomers can immediately ascertain the sun's location simply by examining the orientation of the tail. On the 21st of July, the Hubble Space Telescope acquired the highest resolution image to date of 3 Atlas. At that time, the comet was 277 million miles from Earth, still inbound towards its perihelion in October. The image displays a diffuse glow situated in front of the object, pointing towards the sun. This glow is elongated, approximately 10 times longer than it is wide, forming a structure resembling a teardrop or a jet. Behind the object, in the direction where a tail would normally be streaming, there is nothing. No bright plume, no extended trail of dust, merely a faint gradient of scattered light gradually fading into the surrounding darkness. This forward glow is an anti-tail. While anti-tails are not entirely unknown in comets within our solar system, their occurrence is infrequent. Occasionally, under specific geometric conditions, such as when Earth traverses a comet's orbital plane, we can observe dust particles left behind along the comet's orbital path, which, from our perspective, appear to stretch out in front of the comet. This is an illusion of perspective. However, 3 Atlas is not situated within such a geometric configuration. The viewing angle does not support a perspective-induced effect, and the brightness profile of the forward glow does not correspond to what would be expected from orbital dust. David Jewett, an astronomer at UCLA who led the Hubble observations, meticulously analyzed the surface brightness as a function of distance from the nucleus. In the coma of a typical comet, the brightness diminishes gradually. Dust particles disperse, become diluted, and the intensity decreases following a gentle power law relationship. In contrast, the forward glow of 3 Atlas exhibits a fall-off rate described by a projected power law slope of -3, which corresponds to a 3-dimensional emissivity profile with a radial slope of -4. This is significantly steeper than what is observed in typical solar system comets. It is much steeper. Such a steep decline suggests that whatever is generating the glow is concentrated near its source and dissipates rapidly. This could imply that the material is composed of extremely fine grains that are quickly propelled away by radiation pressure, or that there is active jetting from a specific location on the nucleus, creating a directed plume. Jewett's team interpreted this phenomenon as dust evaporating from the sunward side of the comet. Solar heating would be most intense on the hemisphere facing the sun, causing ice to sublimate and dust to lift off. This dust cloud would expand forward before radiation pressure begins to push it backward. While this is a plausible interpretation, it necessitates the comet shedding material asymmetrically, with the sunward side being considerably more active than the rest of its surface. Such a degree of asymmetry, while unusual, is not impossible. What proves more challenging to explain is the complete absence of a dust tail. If dust is being ejected from the surface in quantities sufficient to produce the visible forward glow, that dust ought to persist. Radiation pressure would propel it outward, and the comet's motion would draw it into a tail, resulting in a discernible feature. Unless the dust particles are exceptionally small, particles less than a few hundred nanometers interact so strongly with light that they are expelled from the comet almost instantaneously, creating a faint haze rather than a distinct tail. However, such minuscule particles are also rapidly degraded by solar radiation, breaking down into even smaller fragments until they become effectively invisible. Alternatively, it is possible that the majority of what we are observing is not dust at all, but gas. Gas does not form persistent tails in the same manner as dust. It disperses, thins out, and becomes transparent once it moves a sufficient distance from the nucleus. But if gas is primarily responsible for the forward glow, this reintroduces questions about composition. What specific gas, at what rate, and why is it so concentrated in one particular direction? Another possibility, explored by Loeb and his colleague Eric Quito in a scientific paper, is that 3 Atlas is generating its own light, rather than merely reflecting sunlight. In such a scenario, the brightness profile would exhibit a different characteristic. Internal energy sources, whether from radioactive decay or some other mechanism, would produce emissions that decrease steeply with distance, simply because one is moving away from the source. This is not as far-fetched as it might initially sound. Certain comets exhibit faint airglow within their comas, which is emission from molecules energized by solar ultraviolet light. However, these emissions are well characterized. We know the expected wavelengths, intensities, and structures. The Hubble image, conversely, is broadband, capturing light across a wide range of wavelengths. Without spectroscopic analysis of that specific forward glow, it is impossible to definitively determine whether it is purely reflected sunlight or if it includes some component of emitted light. What can be asserted with certainty is that the observed structure is anomalous, directed forward, exhibiting a steep fall-off in brightness, and lacking a corresponding tail. Taken together, these features paint a picture that deviates from standard cometary models unless extraordinary circumstances are invoked. And this is where its significance lies. The orientation of this jet, plume, or whatever we are currently calling it, points in the direction of motion. The comet is traveling towards the sun, and the glow extends forward in that same direction. If one were to design a braking system for an interstellar object, releasing material in a forward direction would generate thrust in the opposite direction. While not as efficient as rocket propulsion, over extended periods with continuous mass loss, it could potentially produce measurable deceleration. 3 Atlas has exhibited no measurable non-gravitational acceleration. Multiple research teams have analyzed its trajectory, compiled thousands of positional observations, and found its motion to be consistent with gravitational forces alone. However, such analyses have limitations. Minor accelerations below approximately 15 meters per day, squared, would be indistinguishable from observational noise, and the period of observation has been relatively brief. The comet was only discovered in July, and we have been tracking it for a few months across a portion of its orbit. If it were decelerating slowly, gradually adjusting its trajectory through directed mass expulsion, we might not yet have detected it. Alternatively, the forward jet might be entirely natural, a consequence of how ice sublimates from a rapidly rotating nucleus with an irregular shape. The image alone cannot provide a definitive answer, but when considered in conjunction with the other anomalies, the nickel emissions, the chemical composition, and the trajectory, It contributes to a pattern where each individual observation can be explained by natural phenomena. However, the collective picture becomes increasingly strained. It is conceivable for a comet to possess unusual chemistry, or to exhibit an odd trajectory, or to outgas asymmetrically. But the occurrence of all these features in a single object, the third interstellar visitor ever detected, begins to strain statistical expectations, especially when one calculates the sheer mass of this object. Chapter 6. 33 billion tons of mystery. When an active comet expels gas and dust, fundamental physics dictates a reciprocal response: action and reaction. Material ejected from the surface generates thrust. Although not substantial, it is measurable. A typical comet might experience non-gravitational acceleration on the order of a few hundred meters per day squared. Over weeks and months, this causes the trajectory to deviate from a purely gravitational path. Astronomers utilize these deviations to estimate the amount of mass a comet is losing, and by extension, the mass of its nucleus. More massive objects are more resistant to acceleration. A small nucleus shedding material will veer noticeably, whereas a large one will barely budge. Between May 15th and September 23rd, 227 observatories worldwide meticulously tracked 3 Atlas. Over 4,000 individual position measurements were compiled at the Minor Planet Center, the International Clearinghouse for Small Celestial Body Observations. Richard Cloutier, Peter Vers, and Avi Loeb analyzed this comprehensive dataset. They fitted the observations to a purely gravitational trajectory, calculating the comet's expected position at each moment based solely on the sun's gravity and perturbations from the planets. Subsequently, they scrutinized these calculations for any deviations. The upper limit for non-gravitational acceleration was determined to be less than 15 meters per day squared, potentially much less, perhaps even 0, but definitively below that threshold. This is an astonishingly low value for an active comet that is visibly outgassing. The James Webb Space Telescope detected carbon dioxide escaping from 3 Atlas at a rate of approximately 150 kilograms per second in early August. This translates to 13 tons per day. As the comet drew closer to the Sun through September, this rate likely increased. When mass is ejected at high velocity, the conservation of momentum dictates that the remaining object experiences a force. The gas exiting the surface has an outflow velocity measured by Webb's spectroscopy at around 440 meters per second. Plugging these numbers into the equation, multiplying the mass loss rate by the velocity, and then dividing by the comet's mass, yields the magnitude of acceleration the comet should experience. If 3 Atlas demonstrated negligible acceleration, despite this continuous mass loss, its nucleus must possess sufficient mass such that the resulting thrust becomes undetectable amidst the observational noise. The calculation indicates a minimum mass of 33 billion tons. Consider the magnitude of that number. The initial interstellar visitor, designated Oumuamua, possessed an estimated mass ranging from 10 million to 100 million tons, contingent upon assumptions regarding its density and form. The subsequent celestial body, 2I Borisov, was likely to weigh several hundred million to a few billion tons, inferred from its luminosity and activity level. 3I Phaethon stands at a minimum of 33 billion tons, and potentially more, as this figure represents merely the lower bound. It could be as much as 10 times more massive and still conform to observational data. This renders it 1,000 to 1 million times more substantial than prior interstellar sojourners. This is where statistical anomalies begin to surface. Models detailing the genesis and expulsion of interstellar objects from planetary systems delineate a specific size distribution. Smaller entities are predicted to vastly outnumber larger ones. This is not an arbitrary assertion. It is grounded in our understanding of planetary formation, gravitational interactions, and the mechanisms by which matter is ejected from solar systems. For every kilometer-scale object traversing interstellar space, there should be thousands of objects measuring 100 meters across. For every 100-meter object, there should be thousands more at 10 meters. This distribution adheres to a power law. When we first identified Oumuamua, approximately 100 meters in size, this was in line with expectations. Small objects are commonplace. They are more challenging to detect due to their faintness, but with telescopes continuously surveying the sky, their discovery is anticipated. 2I Borisov, larger and more active, also fits within this framework, being more substantial than Oumuamua, but still within the predicted range of encounters. 3I Phaethon, however, disrupts this pattern. Its minimum diameter, based on the 33 billion ton mass estimate, surpasses 5 kilometers. More realistically, given our knowledge of cometary densities, it is likely between 5 and 10 kilometers in breadth. Objects of this magnitude are expected to be exceedingly rare. Current models suggest that we should observe approximately 10,000 to 100,000 smaller interstellar objects before encountering one of Phaethon's mass. To date, we have identified merely 2. This discrepancy has been labeled a significant anomaly. The term, however, may understate the situation. If 3I Phaethon genuinely spans 5 kilometers or more, and is only the 3rd interstellar object ever catalogued, then either our models of interstellar object populations are fundamentally flawed, or we have experienced an extraordinary stroke of luck, bordering on statistical impossibility, or 3I Phaethon is not a representative sample of the expected population. The lucky hypothesis posits that we have encountered a 1 in 10,000 or worse probability, which, while not impossible, is unsettling. The wrong models hypothesis necessitates a reevaluation of core assumptions concerning planetary system formation and evolution, the ejection of objects into interstellar space, and the mass distribution of celestial debris drifting through the galaxy. This is not an insurmountable challenge, but it would entail substantial revisions to theories that otherwise align well with all our observations. The non-random hypothesis suggests that 3I Phaethon's characteristics are anomalous due to factors beyond mere statistical probability. It may have formed via a rare process that generates large objects more frequently than standard planet formation models predict. Alternatively, it could be a nascent planet, as some researchers have proposed, a substantial solid core ejected early in a solar system's history. Or it might be following a deliberate trajectory that led it to our vicinity, making its detection a matter of design rather than chance. This latter possibility is what causes the most discomfort among astronomers, not because it is impossible, but because accepting it would mean abandoning the principle of exhausting natural explanations before resorting to extraordinary ones. However, the dilemma lies in determining at what point natural explanations become more improbable than the alternative. A comet exhibiting a mass 1 million times greater than anticipated, producing signatures of industrial metals, expelling material forward without a trailing tail, emitting a green glow devoid of the characteristic molecules, aligning with a famous radio signal with a probability of less than 1%, and following a trajectory passing remarkably close to multiple planets. While each anomaly may possess a potential natural explanation, their cumulative effect strains credulity. Furthermore, we have yet to address the most peculiar aspect of its chemical composition. This discovery made headlines precisely because it defied all established rules regarding cometary constituents. Chapter 7. The Chemical Conundrum. On August 6th, the James Webb Space Telescope directed its near-infrared spectrograph towards 3I Phaethon. Operating above Earth's atmosphere, Webb is unimpeded by the water vapor and carbon dioxide that hinder ground-based infrared astronomy, enabling its instruments to detect molecules invisible to terrestrial telescopes. Spectroscopic analysis revealed the presence of carbon dioxide, water, carbon monoxide, and carbonyl sulfide within the comet's coma. While all are expected for an active comet, their proportions were drastically anomalous. The ratio of carbon dioxide to water measured an astonishing 8-to-1. In every other comet ever studied, including the previous interstellar visitor 2I Borisov, water is the dominant volatile component, with carbon dioxide present in minor quantities, typically comprising 5 to 20% of the total volatile inventory. Water ice forms the bulk of cometary material due to the abundance of water in the protoplanetary disks where comets originate. 3I Phaethon completely inverts this scenario. For every molecule of water, there are 8 molecules of carbon dioxide. By mass fraction, the coma consists of approximately 87% carbon dioxide, 9% carbon monoxide, and a mere 4% water. This ratio deviates by 6 standard deviations from the typical value observed in solar system comets, indicating not merely an outlier, but an entirely distinct population. Martin Cordner, the astronomer who led the Webb observations, suggested that such a high concentration of carbon dioxide could imply the comet formed near the carbon dioxide ice line in its parent protoplanetary disk. This is the region surrounding a young star where temperatures drop sufficiently for carbon dioxide to condense into solid ice. Within our solar system, this line is located farther from the Sun than the water ice line. Objects forming between these two boundaries would indeed be rich in carbon dioxide, but even then, water would be expected to be a significant component, not reduced to a mere 4%. Another possibility involves radiation processing. 3I Phaethon has spent billions of years in interstellar space, bombarded by cosmic rays. This radiation can alter surface chemistry, breaking down water ice molecules while leaving carbon dioxide relatively intact. Over extensive periods, this could result in a surface layer enriched in carbon dioxide. However, this would be a surface phenomenon. As the comet approaches the Sun and begins to shed material, one would expect to encounter more typical compositions beneath the processed layer. Spectroscopic data shows no indication of such a transition. The carbon monoxide ratio presents another enigma. At one point, 4 times the abundance of water, it is elevated, but not to the same dramatic extent as the carbon dioxide. Carbon monoxide is even more volatile than carbon dioxide and sublimes at lower temperatures. If the comet were simply warming and releasing ices in order of volatility, carbon monoxide should have appeared first and in high abundance. Instead, carbon dioxide dominates, with carbon monoxide as a secondary component and water lagging significantly. This chemical composition suggests formation conditions dissimilar to anything observed in our solar system. Either the comet originates from a protoplanetary disk with a composition drastically different from the one that formed our planets, or it underwent processes during its journey that transformed its makeup into something unprecedented. Furthermore, there is the matter of polarization. When light scatters off dust particles, it becomes polarized. The degree and direction of polarization depend on the size, shape, and composition of the particles, as well as the viewing angle. Astronomers utilize polarization to infer properties of cometary dust that are difficult to measure directly. A team led by Zach Gray observed 3I Phaethon through polarizing filters over several weeks, measuring polarization as a function of phase angle, the angle between the Sun, the comet, and Earth. The results were unlike any object in the solar system. 3I Phaethon exhibited extreme negative polarization. At small phase angles, the polarized light was oriented perpendicularly to what is observed from every other comet, asteroid, and dusty object. The magnitude of this negative polarization exceeded anything in the existing observational database. Negative polarization can arise when light scatters off particles with specific optical properties. However, achieving the observed degree requires unusual combinations of size, composition, and structure. The dust grains would need to be larger than typical cometary dust, possibly with complex internal structures or unconventional refractive indices. Alternatively, the scattering mechanism may differ from our usual models. If the primary light source is not reflected sunlight, but includes emission from the object itself, the polarization signatures change. Fluorescence from gases can produce polarization patterns distinct from pure dust scattering. However, this again necessitates an explanation for what is emitting light and why. The polarization study, the inverted chemistry revealed by Webb, and the depletion of carbon chains while still allowing for a green luminescence combine to present an object that defies expectations on all fronts. It is possible to construct scenarios where each finding individually makes sense. A comet originating from a carbon dioxide-rich formation region, dust with unusual optical properties resulting from prolonged radiation exposure, or surface chemistry altered by billions of years in space. However, explaining all these factors simultaneously within a single object requires an improbable concatenation of specific conditions. The comet would need to have formed in precisely the right location to be carbon dioxide dominated, then been ejected at the opportune moment to endure billions of years of radiation exposure in interstellar space, subsequently accumulating dust with optical properties unlike anything typically observed. Finally, it would have to enter our solar system on a trajectory that brings it unusually close to multiple planets. The more specific the required conditions become, the less likely the scenario. Adding to the mystery is the detection of cyanogen. Cyanogen, a carbon-nitrogen compound, is not uncommon in comets. However, its presence is noteworthy because early observations detected it in 3I Phaethon, while simultaneously showing a significant depletion of other carbon chain molecules, such as dicarbon and tricarbon. Luis Salazar Manzano of the University of Michigan analyzed spectra from the Kitt Peak Observatory. His team identified evidence of cyanogen emission before the comet was sufficiently close to the Sun to exhibit significant activity, suggesting that cyanogen was present in a volatile form near the surface, easily released with minimal heating. Yet, cyanogen production in comets typically correlates with the presence of complex organic molecules and carbon chains. Discovering it in their absence is unexpected, akin to finding smoke without fire. This suggests that the chemistry may not be following the assumed pathways, or that the molecules were not created through the standard processes of cometary formation and evolution, or that they were introduced via mechanisms we have not yet considered. The chemical signature of 3I Phaethon reads like a cometary enigma, designed to confound. Every measurement reveals properties that, while technically plausible as natural phenomena, collectively strain the limits of what natural processes are known to produce. While chemists debate isotope ratios and spectroscopists analyze emission line profiles, Avi Loeb has been calculating something entirely different. something that relegates the chemistry question to secondary importance, overshadowed by a more immediate concern about the object's future actions. Chapter 8. The Precursor Probe Theory. Loeb commenced with a straightforward geometric calculation. 3I Phaethon passed within 29 million kilometers of Mars on October 3rd, but this was not its closest approach to Mars's orbital path. The minimum orbit intersection distance, a metric quantifying how closely one object's trajectory approaches another's complete orbital path, is a mere 2.7 million kilometers. 2.7 million kilometers sounds immense. It is approximately 7 times the distance between Earth and the Moon. However, in the context of orbital mechanics, particularly for an object traveling at 60 kilometers per second, it is remarkably close. It is sufficiently close that a minor adjustment in velocity could bring the comet into direct contact with Mars. Loeb performed the calculations. A trajectory alteration of 10 to 15 kilometers per second applied during September would reduce this closest approach distance to 0, resulting in an impact with Mars, or, at minimum, a passage within the planet's atmosphere. Naturally, comets do not undergo trajectory changes of this magnitude. The outgassing thrust from a natural comet might induce velocity changes of a few hundred meters per second over several months. Achieving 10 or 15 kilometers per second would necessitate either a catastrophic fragmentation event or active propulsion. However, this is what captured Loeb's attention. If 3I Phaethon is not a singular object, but is accompanied by smaller components, these components do not need to match the main object's velocity. A mothership releasing smaller probes can impart significant relative velocities, causing the probes to separate along slightly different trajectories. While the primary object passes Mars at 29 million kilometers, a probe with the appropriate velocity vector could reach the planet. The Webb telescope measured the outward velocity of gas emanating from 3I Phaethon at 440 meters per second. This is the speed of material naturally vaporizing from the surface. However, if something were deliberately ejected, if a probe separated from the main body using mechanical force rather than thermal evaporation, it could achieve much higher speeds. A velocity of 10 kilometers per second is not unreasonable for a separation maneuver. It is well within the capabilities of conventional rocket propulsion. Even a simple spring-loaded release mechanism could impart a few kilometers per second to a small object. Therefore, Loeb posed the question: if 3I Phaethon released precursor probes in September, could they reach Mars? The answer is affirmative. Depending on the timing and direction, a probe could arrive at Mars anywhere from a few days to a few weeks after separation. Now, we must consider the practical implications. The high-rise camera aboard the Mars Reconnaissance Orbiter was tasked with searching for 3I Phaethon. It was calibrated to detect an object measuring 5 to 10 kilometers across at a distance of 29 million kilometers. However, HiRISE was designed to image Mars's surface and can resolve features down to 30 centimeters. If a smaller object, say 100 meters across, passed closer to Mars, even within a few 100,000 kilometers, HiRISE might detect it. The challenge is that HiRISE was oriented towards the expected position of the main comet. If a precursor probe originated from a different angle and followed a different trajectory, it could approach Mars undetected by the spacecraft specifically monitoring for 3I Phaethon. The sky observations from the Perseverance rover become more pertinent in this context. Those images, showing potentially multiple objects, which were analyzed by Stephen Burns and others, were captured during a period when both the main comet and any potential companions might have been visible. If there were indeed multiple fast-moving objects in those images, and not merely processing artifacts or background noise, we might be witnessing evidence of a dispersed system rather than a single, cohesive nucleus. Loeb extended his calculations further. He considered the scenario following perihelion, after the comet swings around the sun and emerges on the opposite side. The object will be obscured from Earth-based observation from late October through most of November. It reaches perihelion on October 29th at a distance of 202 million kilometers from the sun. During this closest approach, it will experience maximum solar heating, maximum radiation pressure, and maximum stress on any structural components. If it is a natural comet, this is when we would expect to observe significant changes, increased activity, and possible fragmentation. The nucleus could split, releasing fresh ice that dramatically brightens the coma, and outgassing rates could surge as subsurface volatiles reach critical levels. If it is something else, if it possesses the capacity for maneuvering, perihelion offers a strategic opportunity. The gravitational assistance from passing close to the sun could be utilized to alter its trajectory. A minor velocity change at perihelion translates into substantial positional changes months later. This is how spacecraft use gravity assists to reach distant destinations efficiently. Loeb noted that with appropriate thrust at perihelion, 3I Phaethon could adjust its path to intercept Earth. The object will be traveling retrograde, opposite to the direction of planetary orbits. This geometry offers advantages for an intercept trajectory, as it eliminates the need to chase a target and instead involves timing the collision between two objects moving towards each other. A velocity shift of 30 to 40 kilometers per second during October could guide 3I Phaethon, or components thereof, towards Earth between late December and early January. Is a velocity shift of 30 to 40 kilometers per second achievable for a natural comet? Absolutely not. For a spacecraft with propulsion, it depends on the mass and the engine. Chemical rockets would struggle to achieve these numbers for an object as massive as 3I Phaethon. However, we are discussing technology that has potentially traversed interstellar space, employing propulsion systems that are currently beyond our comprehension. Loeb was precise in his phrasing. He did not claim that 3I Phaethon would maneuver towards Earth. Rather, he highlighted the existence of the opportunity, suggesting that if the object possesses such capabilities, this is the time and manner it would employ them. He then added a statement that was widely reported by news outlets covering the story. If 3I Phaethon maneuvers towards Earth when it reappears from behind the sun, financial markets may crash. Consider the implications of this statement. Beyond the immediate panic that news of an object heading towards our planet would instigate, there are deeper implications. Confirmation that we are dealing with technology, that something artificial has crossed interstellar space and is now approaching Earth, that we are not alone, and that whatever exists out there is aware of our presence. Markets crash due to uncertainty, due to fundamental shifts in our understanding of the world. The discovery of artificial interstellar technology would represent the most profound uncertainty in human history. Even if the object posed no direct threat and its intentions were entirely benign, the knowledge that advanced civilizations exist and can reach our solar system would fundamentally reshape every assumption underlying our economic, political, and social structures. Loeb's statement was not an act of fear-mongering. It was an acknowledgement that the implications extend far beyond the realm of astronomy. This is why the Mars observations are so critical, and why the silence from NASA and ESA feels significant. Because at this moment, 3I Phaethon is approaching a juncture where, if it intends to do anything unexpected, this is the window of opportunity. We will not know what has transpired until it emerges from solar occultation weeks from now, potentially having altered its course, potentially having released objects beyond our tracking capabilities, potentially having demonstrated capabilities that compel us to abandon the comfortable assumption that it is merely an unusual comet. Loeb refers to it as the Trojan horse, an innocuous-looking visitor that might harbor devastating consequences concealed within its seemingly natural exterior. Chapter 9. Behind the Sun, the Danger Window. Loeb has devised a scale, the Loeb scale, ranging from 0 to 10, to quantify the likelihood of an object being artificial rather than natural. 0 signifies definitively natural, a mass of ice and rock adhering to predictable physics, with chemistry consistent with known processes. 10 signifies definitively artificial, an object exhibiting unambiguous technological signatures, maneuvering in ways that require propulsion, emitting signals, or displaying structures that cannot be explained by natural means. Most objects, such as asteroids, comets, and meteoroids, all the debris drifting through space, score 0 because nothing about them suggests technology. The initial interstellar visitor, designated Oumuamua, is currently ranked between 3 and 5 on our scale of certainty, a rating dependent on which observational data points we prioritize. Its peculiar form, its acceleration despite lacking discernible gas expulsion, and its erratic spinning motion all contributed to elevating it from a score of 0, though not sufficiently to confirm its non-natural origin. The object known as Three-Eyed Atlas now holds a rating of 4. It is not a 0 due to the sheer volume of anomalies observed. These include its orbital alignment with planetary bodies, its unusual chemical composition, the presence of nickel without accompanying iron, a forward-directed jet with no discernible tail, and a significant discrepancy in its estimated mass. While any single one of these features might be attributable to natural phenomena, their collective occurrence significantly increases the probability of an artificial source. It does not yet reach a score of 10 because we lack conclusive evidence. No artificial radio transmissions have been detected, no deliberate maneuvers observed, and no photographic evidence of geometric construction has surfaced. The object continues to exhibit characteristics consistent with a comet, allowing for natural explanations, however improbable they may seem. Our current assessment places 4 in an ambiguous middle ground, leaning more towards a natural explanation, but with enough peculiar attributes that the possibility of artificial origin cannot be discounted. However, this classification could undergo a dramatic revision based on events unfolding in the coming weeks. October 29th marks the perihelion, the point at which the comet achieves its closest proximity to the Sun, at approximately 1.4 astronomical units, situated just within the orbital path of Mars. At this precise moment, from Earth's vantage point, the object will be positioned directly behind our star. The Sun's apparent diameter in our sky spans roughly half a degree. Three-Eyed Atlas will transit through this region of intense solar glare. Ground-based telescopes will be rendered incapable of observation. Space-based observatories, such as the Hubble and Webb telescopes, must avert their gaze from pointing too closely to the Sun to safeguard their sensitive instruments. We effectively enter a period of blindness. This observational blackout will persist from late October through the majority of November. The exact duration will be contingent upon our viewing geometry and the comet's apparent brightness. Conservatively, we anticipate a loss of direct observation for a minimum of 3 weeks. During these 3 weeks, the object will experience peak solar heating. Its thermal stresses will reach their maximum, and if it possesses technological origins, it will have ample privacy to engage in whatever functions it was designed for. Upon its reappearance, we will be meticulously searching for any alterations. luminosity serves as our primary indicator. Should the comet fragment or undergo a significant outburst, a noticeable increase in brightness is expected. Comets originating within our solar system occasionally amplify their brilliance by several magnitudes during their perihelion passage. If Three-Eyed Atlas replicates this behavior, it would strongly suggest the dominance of natural processes. Conversely, if it fails to brighten, maintaining its relative stability or even diminishing in luminosity, that would be a highly intriguing development. It could signify a more robust structure, less susceptible to thermal stress than typical comets. Trajectory constitutes our second key indicator. If the object re-emerges on a path consistent with gravitational predictions, following the orbital trajectory calculated from pre-perihelion observations, this would bolster the natural interpretation. However, any deviation, any alteration in velocity or direction not attributable to gravitational influences would rapidly elevate its standing on our rating scale. Spectroscopy will be instrumental in revealing compositional shifts. Will the surface chemistry undergo a transformation? Will new materials be exposed? Will the ratio of volatile compounds differ from our prior measurements? And regarding its structure, once Three-Eyed Atlas becomes visible again in early December, telescopes will immediately commence photographic documentation. Will it present the same appearance? Will the forward jet remain evident? Will there be any indication of fragmentation or splitting? Meanwhile, Lowe is not merely engaged in theoretical calculations. He is actively monitoring the celestial sphere. The Galileo project operates 3 observatories, situated in Massachusetts, Pennsylvania, and Nevada, respectively. These facilities are equipped with wide-field cameras, infrared sensors, and automated detection algorithms specifically designed to identify aerial phenomena that deviate from conventional aircraft or known natural objects. The project's overarching objective is the study of unidentified anomalous phenomena, or UAP, previously referred to as UFOs. However, with Three-Eyed Atlas approaching its perihelion, Lowe has implemented a specialized monitoring protocol. Should the object be a mothership, capable of deploying smaller probes toward Earth as it completes its solar trajectory, those probes would arrive weeks to months later. The period from December through January represents a potential window for a surge in unexplained aerial activity. The instruments employed by the Galileo project will operate continuously, meticulously logging any unusual occurrences, discerning patterns, and seeking out objects exhibiting speeds exceeding those of satellites, displaying flight characteristics beyond the scope of current aerospace technology, or appearing in numbers or at timings that correlate with the perihelion passage of Three-Eyed Atlas. While this may sound like science fiction, it draws from scenarios commonly found in speculative narratives. The crucial distinction lies in our engagement with actual data, rigorous calculations, and tangible objects that we can photograph and measure. If Lowe's hypotheses prove incorrect, and Three-Eyed Atlas is merely an unusual comet, with all its anomalies possessing mundane explanations, the Galileo project will detect nothing out of the ordinary. The object will re-emerge from behind the sun, perhaps slightly brighter, possibly fragmented, following its predicted course. The observed nickel emissions will be elucidated through some exotic chemical process. The observed trajectory alignment will be recognized as a consequence of selection bias in the types of interstellar objects we are inclined to notice. Life will continue. However, if Lowe is correct, even partially, December could mark one of the most pivotal months in human history. This significance would not stem from scenarios of invasion or hostile intent. Lowe is careful to avoid such framing. Even artificial constructs can function as benign scientific probes dispatched by civilizations with no inclination towards interference. Rather, the profound impact would arise from the confirmation that fundamentally alters our understanding. Every assumption about our cosmic standing would be re-evaluated. Every question regarding our solitude would be definitively answered. Every strategic decision concerning resource allocation and our future trajectory would be made within a framework that acknowledges the reality of interstellar travel, the existence of other intelligences, and our not being singularly special in the grandest sense. Yes, the JUICE spacecraft, currently en route to Jupiter, is scheduled to observe Three-Eyed Atlas in late November. Between November 2nd and 25th, JUICE will direct its instruments toward the comet shortly after its perihelion, as it emerges from the sun's glare while still intensely active. JUICE is equipped with cameras, spectrometers, and particle sensors. Although it will be positioned farther from the comet than Mars was, it benefits from observing during a period of peak activity when the object's signatures are most pronounced. The data transmitted by JUICE will not reach Earth until February. The spacecraft will be on the opposite side of the Sun from our planet, utilizing its high-gain antenna as a heat shield and communicating via a slower backup system. Consequently, we will endure months of waiting for these observations to download and undergo processing. Nevertheless, they are forthcoming and may reveal what Three-Eyed Atlas was doing while concealed from Earth, how it appeared at its most active juncture, and whether any changes occurred that necessitate our understanding. For the present, however, we remain in darkness, both literally and figuratively. The object that has perplexed astronomers for months is on the verge of becoming invisible, obscured by the overwhelming brilliance of our star, engaging in whatever activities it undertakes when unobserved. And upon its reappearance, should it present itself differently, displaying any indication of deliberate action, Lowe's assessment will shift from a rating of 4 to 5, or perhaps even higher. The questions we have been posing regarding its potential artificial nature will transform into inquiries about its intentions and our appropriate response. Chapter 10. Information Withheld. A predictable pattern governs how space agencies disseminate their discoveries. Press releases are meticulously crafted. Scientists provide interviews. Raw data is uploaded to public repositories. Social media platforms share highlights. This process is designed to foster transparency, cultivate public engagement, and justify the financial investment that underpins these missions. When this established rhythm falters, when scheduled observations are conducted, but their outcomes are not immediately published, when inquiries are met with evasive statements about ongoing analysis, public attention is invariably drawn. NASA's official listing for Three-Eyed Atlas enumerates the instruments that have observed or are slated to observe the object, including Hubble, Webb, TESS, SWIFT, SphereX, Perseverance, Mars Reconnaissance Orbiter, Curiosity, Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, SOHO, and ESA's JUICE. This represents an impressive array of assets. Virtually every operational space telescope and planetary mission has, at some point, been directed towards this object. However, the release of data does not align with the observation schedule. Webb's spectroscopic data from August was published promptly, appearing as a preprint within weeks. Hubble's July image was made public. Results from SphereX concerning carbon dioxide emissions were shared. Then, as October commenced, the flow of information ceased. The observations conducted by Mars-based assets between October 1st and 7th should have been the most straightforward to release. Mars orbiters routinely make their imagery accessible within days. The HiRISE website typically updates with new Mars surface photographs every few days, sometimes daily during active observation campaigns. Yet, nothing from the three-eyed Atlas flyby has materialized. The European Space Agency operates under different administrative frameworks than NASA, with distinct funding streams, oversight mechanisms, and public communication mandates. The simultaneous silence from both agencies concerning the same target suggests a degree of coordination. This coordination could imply collaboration, with scientists from both agencies working together and agreeing to defer any statements until all data has been thoroughly analyzed. This approach is reasonable for complex observations where preliminary findings might be prone to misinterpretation. Alternatively, coordination could signify consultation, involving the discovery of something unexpected that necessitates discussion regarding its presentation, the appropriate context to provide, and any further verification required before public disclosure. The silence emanating from Simeon Schmaus, the astrophotographer who claimed to have captured early glimpses in the October 1st imagery, adds another layer of complexity. Amateur observers typically hasten to share their findings. The scientific community thrives on rapid discourse, crowdsourced verification, and collaborative analysis. When an individual becomes reticent after making a compelling claim, it usually indicates one of two possibilities. Either an error was discovered, leading to embarrassment, or something significant was found, and preparations are underway for a more detailed presentation. Schmaus has neither retracted his observations nor posted corrections. He has simply ceased commenting. In the interim, amateur astronomers continue their work with the available data. The publicly accessible Perseverance images from those October nights remain available for examination. Any individual possessing image processing software can download, stack, and analyze these images for the presence of moving objects. Multiple independent analysts have now corroborated Stephen Burns's finding of at least one rapidly moving object consistent with three-eyed Atlas. The ongoing debate centers on the potential presence of additional objects. Some observers clearly perceive them, while others attribute the apparent extra lights to artifacts generated by stacking algorithms, cosmic ray impacts that coincidentally appear near the comet's trajectory, or background asteroids. In the absence of high-resolution data from HiRISE and the ESA orbiters, and without official confirmation or denial, the question remains unresolved. What we are observing is a discernible pattern. Official channels are constrained by review processes and institutional caution. Amateur observers are filling this information void with varying degrees of scientific rigor and reliability, and the object itself continues to generate more questions than answers. Consider the aspects that remain unknown despite months of observation. The precise dimensions of the nucleus, with estimates ranging from less than 1 kilometer to over 10 kilometers, depending on assumptions about its albedo, and whether we are primarily observing the nucleus or an expanded dust coma. The rotational rate is also uncertain. Some observations suggest rapid rotation, while others reveal no clear periodicity. Understanding its spin rate provides insights into its structural integrity, indicating whether it is a single solid body or a loosely aggregated collection of material. The origin of its outgassing, whether material is venting from discrete jets or from broad surface areas, is another unknown. Discrete jets imply localized volatile deposits or structural features, whereas broad emission suggests a more uniform surface composition. The degree of fragmentation, if any, also remains unclear. Has the nucleus fractured into multiple pieces? Are there companion fragments traveling alongside the main body, or is it structurally intact? These are fundamental questions that the Mars observations were intended to address. At a resolution of 30 kilometers, HiRISE should readily distinguish between a single compact object and a fragmented or multi-component system. Spectroscopy from Mars Express and ExoMars should reveal regional compositional variations, should they exist. The instruments functioned as intended, the observations were executed, and the data resides somewhere within agency archives. We are simply not privy to it. There are plausible, innocent explanations. Data pipelines genuinely experiencing backlogs due to technical issues, scientists conducting thorough analyses prior to releasing statements, and bureaucratic delays unrelated to the substance of the findings. Then there are less innocent explanations. Uncertainty regarding how to characterize unexpected discoveries, consultations concerning whether preliminary observations warrant broader discussion before formal publication, and institutional hesitation to issue claims that might later necessitate embarrassing retractions. Finally, there are concerning explanations. The discovery of features that challenge comfortable assumptions, evidence of structures or behaviors that defy categorization as natural phenomena, and observations that, if released without context, would incite precisely the kind of speculation and public apprehension that space agencies strive to prevent. We do not know which of these categories applies. This is the crux of the problem. The absence of information creates a void that speculation inevitably fills. What we can state with certainty is that the upcoming weeks hold immense significance. Three-eyed Atlas will emerge from behind the Sun in late November or early December. Ground-based telescopes will immediately commence photographic observations. Amateur astronomers will be vigilantly watching. Professional observatories have allocated observation time. If the object appears unchanged, if its trajectory aligns with predictions, and if its brightness and spectral signature remain consistent with our prior measurements, the natural comet explanation will gain considerable traction. However, if any alterations are detected, such as evidence of maneuvering, structural modification, unexpected brightening, or novel compositional signatures, the artificial hypothesis will be strengthened. JUICE is slated to observe the comet in late November, during its peak post-perihelion activity. Europa Clipper, currently en route to Jupiter, may also conduct observations depending on its orbital geometry and mission priorities. These spacecraft will observe the comet from angles and distances inaccessible to Earth-based instruments. Their data will eventually reach us, undergo processing, and ultimately contribute to our understanding. But eventually is not now. At this precise moment, we exist in a gap between what has been observed and what has been disclosed, a gap between amateur discoveries and official validation, a gap between the questions we are posing and the answers that reside, somewhere, within inaccessible data files. And as we wait within this interim, Three-eyed Atlas continues its cosmic journey, approaching the Sun, heating up, becoming more active, potentially engaging in activities whose nature we will only comprehend weeks from now, upon its reappearance, when we observe what has changed. And so, we find ourselves waiting, gazing at an empty sky where something extraordinary is presently concealed behind our Sun. Three-eyed Atlas is out there at this very moment, closer to our star than it has been in billions of years, absorbing gigawatts of solar energy, potentially fragmenting, potentially maneuvering, or potentially doing nothing more remarkable than what comets have done since the solar system's inception. We have meticulously traced its trajectory from the distant reaches of space, calculated its position when the WOW signal was detected on Earth, measured the improbable ratios within its chemical makeup, documented the presence of metals that should not be there, and mapped the tail that points in an unexpected direction. We have quantified the statistical improbabilities, compiled the anomalies, and arrived at a juncture where certainty feels impossibly remote. Perhaps it is merely a comet, albeit an unusual one, ultimately a natural object governed by natural laws. The anomalies will be resolved. The missing data will emerge and provide clarification. December will arrive, and the object will appear precisely as anticipated, perhaps a touch brighter, following its predicted course, reaffirming that the universe remains comprehensible. Or perhaps we are witnessing an event that will fundamentally rewrite every assumption we hold about our place in the cosmos. Regardless, the ensuing weeks will provide the answer, and we will be present to witness it. Thank you for your continued engagement with this narrative, for venturing into uncertainty alongside these questions, and for your willingness to embrace mystery rather than demanding facile answers. If you have found this exploration valuable, please consider liking and subscribing to ensure you are informed when the object reappears and we finally ascertain its nature. As always, this content is intended for educational and entertainment purposes. The scientific principles are valid, the observations are documented, but the interpretations remain speculative. We are exploring possibilities, not making definitive pronouncements. We encourage you to conduct your own research and to question everything, including the information presented here. For now, Three-Eyed Atlas proceeds in silence behind the sun. December draws near. Amateur telescopes stand ready. Professional observatories have allocated their time. The Galileo Project's instruments are actively recording. And somewhere within the vast darkness, an object originating from another star continues its solitary journey, indifferent to our inquiries, our theories, and our hopes and fears regarding its potential significance. Sleep well, dream of distant stars, and remember that the universe has perpetually held more strangeness than we have ever imagined. Good night. Picture this at this precise moment. 620 light-years away, a celestial body the size of Jupiter is undergoing a voracious consumption. Not a gradual process, but a violent one. It is absorbing 6 billion tons of gas and dust every single second. Material that is feeding something that should not exist, something that blurs the distinction between what we define as a planet and what we define as a star. Meanwhile, closer to home, on a world we have studied for decades, a robot approximately the size of a car has discovered something within a rock that may very well be the definitive trace of extraterrestrial life. And in laboratories across our planet, scientists have just shattered a barrier that has stood for the entire history of quantum computing, successfully constructing a machine capable of perpetual operation, theoretically speaking, thereby unlocking possibilities previously believed to be decades away. However, what truly lends this week its peculiar character is that alongside these cosmic revelations, we are also uncovering secrets within our own bodies that we never suspected. Adipose tissue, the kind we carry daily, has been implicated in directly transmitting chemical messengers to our brains, messengers that may be instrumental in forming the very plaques that lead to memory loss. And if we cast our gaze far back into the annals of time, to an era preceding all of this significance, before humanity, before the age of dinosaurs, and even before the first tree emerged, there existed a dominion that held sway over this planet for nearly 1 billion years. It was neither animal nor plant, but fungi, the unseen architects responsible for constructing the world we now inhabit. This is not science fiction. This is the reality of this week. If you find yourself captivated by these mysteries, please engage with the like button and subscribe. Then, kindly inform me in the comments where you are listening from, what time it is in your location, And which of these discoveries most profoundly challenges your understanding of reality? Should you wish to contribute to the growth of our community, please share this content on X, Facebook, Reddit, or via your messaging platform. Thank you for your unwavering support. Chapter 1. The Leopard-Spotted Rock. On the 23rd of July, 2024, an apparatus known as Perseverance engaged a drill bit against a rock on the surface of Mars. This particular rock had been assigned the designation Chava Falls, a name chosen by the team on Earth who had been closely monitoring this specific stone for several months. Their reasons for this focused attention were well-founded. The rock was situated at the periphery of what was once a river valley, a channel that had evidently carried water rushing into a crater that, more than 3.5 billion years ago, had contained a lake. However, it was not solely its geographical context that prompted their decision to halt and investigate. It was the peculiar pattern adorning the surface. Mottled patches, dark circular forms ringed with paleness, were dispersed across the reddish geological material, reminiscent of the distinctive coat of a leopard. This type of formation had never been previously observed. A specialized drill extracted a cylindrical segment of rock, approximately the diameter of a pencil, which was then securely encased within a tube for potential transport back to Earth. Following this, the core investigation commenced. The autonomous vehicle, or rover, was equipped with instruments capable of analyzing the chemical composition of the rock without breaching the containment tube. The discoveries made sent reverberations through the scientific community, effects that continue to propagate. The dark spots were found to contain iron and phosphate. Interspersed within the pale bands of calcium sulfate, indications of hematite, the mineral responsible for Mars' characteristic red hue, were detected. However, within this particular specimen, a transformation had occurred, altering the red coloration to white. This specific type of chemical alteration results in the release of iron and phosphate. Furthermore, these reactions can serve as an energy source, the very kind utilized by microscopic organisms. On the 10th day of September, 2025, a scholarly article was published in the journal Nature. The authors had dedicated an entire year to scrutinizing the collected data, conducting various tests, and rigorously verifying their conclusions. They detailed the presence of two distinct mineral compounds, vivianite and greigite, identified as iron phosphate and iron sulfide, respectively. On our planet, these minerals typically originate in environments deficient in oxygen, where microbial life actively metabolizes organic matter, a clear indication of biological processes supporting survival. The observed patterns and the chemical makeup were consistent. Every aspect of this rock suggested a process that, if found on Earth, would unequivocally point to a biological origin. The acting administrator of the National Aeronautics and Space Administration convened a press conference. Following a year of thorough review, he stated that no alternative explanation could be identified. He declared to the global audience that this could very well represent the most compelling evidence of life ever discovered on Mars. While not definitive proof, it was the closest tangible indication yet obtained by their robotic instruments. The media responded with widespread excitement. Headlines proclaimed the discovery of extraterrestrial microbes and evidence of ancient Martian civilizations. However, the scientific contingent adopted a more measured approach, employing a term that, while sounding somewhat unconventional, carries substantial scientific weight: potential biosignature. This designation signifies something that might have been produced by living organisms, but necessitates further investigation before any conclusive pronouncement can be made. It is at this juncture that the narrative takes a disheartening turn. The analyzed sample remains secured within the internal storage of the Perseverance rover, sealed in its protective tube, alongside 24 other samples gathered from various locations across Jezero crater. To definitively ascertain the origin of these peculiar leopard-like markings, scientists require the physical return of this rock to Earth. They need to subject it to analysis using instruments far more sophisticated than any currently deployable on Mars. This includes the necessity of mass spectrometers, electron microscopes, and other specialized equipment typically housed within extensive laboratory facilities. A program has been established with the specific objective of achieving this very goal. It is known as Mars Sample Return. Unfortunately, this ambitious endeavor is currently facing significant challenges. The estimated cost has escalated dramatically, projected to be somewhere between $8 and $11 billion. The anticipated completion date has been extended to 2040, or even beyond. Subsequent to these developments, changes in political administrations, shifts in governmental priorities, and budgetary limitations have further impacted the program. As of the present, the Mars Sample Return Initiative exists in a state of considerable uncertainty, neither officially abandoned nor fully operational. Consequently, we possess a rock on Mars that may harbor evidence of ancient life, yet there is no clear pathway for its retrieval. Chapter 2: The Celestial Body That Consumes Like a Star. Located 620 light-years from Earth, within the constellation known as Chameleon, exists an astronomical object that defies conventional behavior. It is identified by a designation rather than a personal name. Chi 1107-7626, a sequence of alphanumeric characters used by astronomers to systematically categorize celestial discoveries. This object possesses a mass estimated to be between 5 and 10 times that of Jupiter, the colossal planet in our own solar system. This significant mass firmly places it within the classification of a planet. However, it does not orbit a star. Instead, it drifts in isolation through the cosmic expanse. It is one of what we surmise to be trillions of rogue planets traversing the galaxy, unattached and floating in the vast emptiness between stellar bodies. For many years, scientists held the belief that these errant celestial bodies were cold, inert, and dormant entities, either formed in proximity to a star and subsequently ejected, or perhaps coalesced from gas clouds too small to initiate nuclear fusion, destined to remain perpetually dim and unremarkable. Chi 1107 has demonstrably contradicted these long-held assumptions. In the spring of 2025, astronomers directed the powerful capabilities of the European Southern Observatory's Very Large Telescope toward this anomalous object. What they observed was a surprising scene: a young world still enveloped by a swirling disk of gas and dust, the residual material from its formation. This disk was gradually supplying the planet through a process known as accretion, where matter accumulates onto its surface, incrementally increasing its mass. This is a common and expected phenomenon, representing the natural mechanism by which planets grow. However, by the month of August, the situation underwent a dramatic transformation. The planet began to aggressively consume its surrounding disk. This was not a gentle process. It was characterized by an extraordinary surge of activity. The rate of accretion dramatically accelerated, becoming 8 times faster than it had been merely months prior. 6 billion tons of material were being ingested every single second, pouring into this solitary world suspended in the void. To provide a sense of scale, envision the entire mass of Mount Everest vanishing into this planet every few seconds. This intense period of rapid accumulation persisted for a minimum of 2 months. By the time the relevant scientific paper was published on the 2nd day of October, 2025, the phenomenon was still ongoing. The lead researcher, a scientist named Victor Almendros Abad, articulated a sentiment that perfectly encapsulates the strangeness of the situation. He explained that people often perceive planets as tranquil and stable worlds. However, he continued, this discovery reveals that planetary mass objects freely drifting in space can indeed be dynamic and captivating environments. Captivating may indeed be an understatement. The activity exhibited by Chi 1107 is a phenomenon previously documented only in nascent stars and brown dwarfs, celestial bodies possessing sufficient mass to generate complex magnetic fields. This represents the most potent accretion event ever recorded for a planetary mass object in the history of astronomical observation. The situation becomes even more peculiar. The research team detected evidence of magnetic fields actively driving this influx of material. Powerful magnetic fields were observed to be channeling gas and dust towards the planet's surface, akin to invisible cosmic thoroughfares. This is a process typically associated with stars, not planets. Stars possess the requisite mass and internal dynamics to generate substantial magnetic fields. Planets, particularly rogue planets drifting in isolation, are not expected to exhibit such capabilities. Yet, here it is, occurring, observable, and undeniably present. The investigation also revealed the presence of water vapor in the planet's atmosphere during this period of intense activity, along with hydrocarbon molecules whose structural configurations shifted as the accretion process intensified. These findings indicated signatures of heat and turbulence, actively reconfiguring the chemical composition of the surrounding disk. Scientists are now re-examining a fundamental question they believed had been definitively answered: the origin of rogue planets. The two predominant theories propose either ejection, where a planet forms around a star and is subsequently expelled due to gravitational interactions, or direct collapse, where a cloud of interstellar gas collapses under its own gravity, but fails to achieve the critical mass necessary to ignite nuclear fusion. If ejection is the primary mechanism, these planets should be cold and inert, their formation disks long dissipated. However, Chi 1107 still possesses its disk and continues to grow, behaving in a manner consistent with having formed in situ, condensing from a cloud much like a star would, albeit falling short of the mass threshold required for fusion. This observation blurs a formerly distinct boundary. What, precisely, differentiates the smallest stars from the largest planets? The defining characteristic has traditionally been fusion, the ability of an object to sustain hydrogen burning within its core. However, if objects within the planetary mass range can form, grow, and utilize magnetic fields in ways analogous to stars, then perhaps the dividing line is not as rigid as previously assumed. It is conceivable that a spectrum exists, a gradual gradient between planet and star, with rogue worlds like Chi 1107 occupying an intermediate position, defying our established classifications. The researchers hypothesize that we are currently witnessing planetary formation in real time, observing a world actively constructing itself within the darkness between stars, and that this process is far more dynamic and violent than anyone had previously anticipated. Chapter 3: The Machine That Never Ceases. Within the confines of a laboratory at Harvard University, a remarkable piece of machinery has been in continuous operation for over 2 hours. This duration might not seem exceptionally long until one comprehends the nature of the device itself. It is a quantum computer, and throughout the entire history of quantum computing, these machines have been plagued by a critical inherent flaw: they cease to function. This cessation is not due to an intentional shutdown, but rather because the fundamental building blocks, the quantum bits or qubits that enable their operation simply dissipate. In the terminology of physicists, they undergo decoherence, meaning they lose their quantum properties and become inert. Early quantum computers could maintain their operational state for mere milliseconds. The most advanced systems managed to extend this period to approximately 13 seconds. Following this, they required a complete restart and reset, beginning the process anew. The team at Harvard, under the leadership of Professor Mael Lucan, has engineered a fundamentally different system. In September of 2025, they published their groundbreaking findings in the journal Nature. Their quantum computer comprises 3,000 qubits and possesses the capability to operate continuously, without interruption or the need for restarting, for as long as they elect to maintain its power supply. Theoretically, its operation could be sustained indefinitely. This development represents not a minor improvement, but a fundamental breakthrough that profoundly alters the capabilities of quantum computers. The challenge they have successfully addressed is as follows. Quantum computers function by manipulating atoms or subatomic particles, maintaining them in exquisitely delicate quantum states where they can represent multiple values simultaneously. This inherent property is the source of their immense power, enabling them to solve certain computational problems exponentially faster than conventional or classical computers. However, these quantum states are inherently fragile. They necessitate extremely low temperatures, often approaching absolute zero, and require stringent isolation from all forms of environmental interference, including vibrations, stray electromagnetic fields, and any external disruption. Despite these elaborate protective measures, the qubits eventually fail. They leak information, their quantum states collapse, the quantum coherence dissolves, and the computational process terminates. The Harvard team dedicated 5 years to tackling this formidable problem. They devised a novel method utilizing what they term an optical lattice conveyor belt and optical tweezers. These are sophisticated tools employing focused laser light, capable of precisely capturing and relocating individual atoms with extraordinary accuracy. The pivotal breakthrough involved developing a method to replenish the qubits while the machine remained operational. As qubits depart the system, new atoms are introduced to substitute them. This system can introduce 300,000 atoms per second, a rate that substantially surpasses the rate at which qubits are lost. Consequently, there is now fundamentally no limit to the duration for which these quantum computers can operate. One of the researchers, a gentleman named Tout Wang, made a striking statement during an interview. He acknowledged that there is still a considerable distance to cover in terms of scaling from their current achievements, but he emphasized that the roadmap for future development is now clearly defined based on the experimental breakthroughs achieved at Harvard. Clear roadmap. These words carry significant weight in a field where progress has often been uncertain and projected timelines have been repeatedly missed. Another collaborator, a physicist from MIT named Vladimir, offered a more precise perspective. He indicated that prior to this advancement, it was generally believed that continuously operating quantum computers were at least 5 years away from realization. Now, he suggests, the timeline appears much closer, more within the horizon of 2 to 3 years. Consider the implications of this acceleration. Within 2 to 3 years, we may possess quantum computers that function in a manner comparable to the everyday classical computers we currently utilize. These would not be machines that operate for brief intervals before requiring a restart, but rather systems that remain active, accumulating results, and capable of undertaking complex problems necessitating sustained computation. The ramifications of this technological leap extend across a multitude of scientific and industrial domains. This includes drug discovery, where quantum computers could simulate molecular interactions currently beyond the capacity of classical calculation. In cryptography, they could potentially break encryption schemes that safeguard global communications. In the realm of artificial intelligence, they could optimize neural networks in ways currently unattainable. Other affected areas include material science, financial modeling, and climate prediction. Essentially, any domain where complexity surpasses the computational limits of traditional computing paradigms. However, there exists another significant dimension to this narrative. Google also recently made notable news in the quantum computing sphere, utilizing a 58-qubit quantum computer to create and observe what is termed a Floquet topologically ordered state. This represents a phase of matter that had been theorized but never empirically observed. It exists exclusively when a quantum system is subjected to periodic rhythmic driving, thereby generating a non-equilibrium state that cannot be adequately described by conventional physics. The researchers witnessed exotic particles transforming in real time, confirming theoretical predictions about the behavior of matter when pushed far beyond its equilibrium state. These are precisely the kinds of groundbreaking experiments that quantum computers enable. They facilitate not merely faster computations, but also entirely novel avenues for exploring the fundamental principles of physics itself. Chapter 4. The adipose tissue that communicates with your brain. Something is currently occurring within your body that scientists have only recently begun to understand. Your adipose tissue, the fatty material that cushions your internal organs and stores energy, is not a passive entity. It is actively communicating, not through spoken language, of course, but through chemical signals. These signals are delivered in minuscule packages enclosed within membranes that travel through your bloodstream. These packages are referred to as extracellular vesicles, and they transport their contents, lipids, proteins, and genetic instructions. They possess the ability to permeate the walls of blood vessels and can cross biological barriers that most molecules are unable to penetrate. Furthermore, researchers have now definitively established that some of these vesicles successfully reach your brain. A research team at Houston Methodist, led by scientist Stephen Wong, published their findings on the 3rd day of October, 2025. They collected adipose tissue samples from individuals who were both lean and obese. From these samples, they isolated the vesicles released by the tissues and meticulously examined their internal composition. The lipid content differed significantly. Specific fat molecules were found in greater abundance within vesicles originating from obese individuals. These molecules bear names such as lysophosphatidylcholine and sphingomyelin. Subsequently, the researchers performed a clever experiment. They exposed these vesicles to amyloid beta peptides. These are the proteins that form the characteristic sticky plaques observed in the brains of individuals diagnosed with Alzheimer's disease. The vesicles derived from adipose tissue of obese individuals significantly accelerated the clumping of these proteins, increasing the aggregation process substantially. The lipids they carried acted as catalysts, hastening the very aggregation process believed to drive neurodegeneration. This is not merely a correlation. It demonstrates a direct mechanism. The researchers provided evidence that adipose tissue can transmit signals directly to the brain, and these signals can influence the rate at which the hallmark pathology of Alzheimer's disease develops. For years, obesity has been recognized as a risk factor for Alzheimer's disease, but the connection remained indistinct and indirect, thought to be mediated through factors such as inflammation or insulin resistance. This study establishes a direct causal link. Adipose tissue releases vesicles. These vesicles traverse the blood-brain barrier. The vesicles carry lipids that promote the formation of amyloid plaques. This represents a biological pathway, a circuit connecting the body's energy storage system to one of the brain's most devastating diseases. Almost concurrently, another research team at Purdue University published related findings. They focused their investigation on cells within the brain itself, specifically microglia. Microglia are the immune cells within the brain that are responsible for protecting neurons. In healthy brains, microglia actively patrol the neural landscape, clearing cellular debris, combating infections, and maintaining a state of equilibrium. However, in the brains of Alzheimer's patients, the microglia located in close proximity to amyloid plaques exhibited distinct abnormalities. They were enlarged and engorged with lipid droplets, indicating the accumulation of fat within the cells themselves. The research team, led by Professor Gareth Chopra, discovered that these lipid-laden microglia were incapacitated, unable to perform their essential functions. They could no longer clear plaques, nor could they effectively protect neurons. They were, in essence, rendered immobile by their own excessive lipid burden. The team meticulously traced the biochemical pathway involved. When microglia encounter amyloid plaques and experience inflammation, they begin to produce free fatty acids. Under normal circumstances, these free fatty acids would be utilized as an energy source. However, in the diseased state, a critical malfunction occurs. An enzyme known as DGAT2 converts these free fatty acids into triacylglycerol, a stored form of fat. This conversion process proceeds at such a high rate that the microglia become overwhelmed. Consequently, lipid droplets accumulate within the cells, impeding their movement and rendering them non-functional. Chopra aptly described these intracellular accumulations as lipid plaques, a term that deliberately echoes the amyloid plaques that have historically been the primary focus of research, yet represents a distinct pathological issue that has been overlooked for over a century. The intriguing aspect of this discovery lies in the researchers' successful testing of two specific molecules. One molecule was designed to inhibit the DGAT2 enzyme, while the other was developed to promote its degradation. The latter approach proved effective, leading to a reduction in fat buildup within the microglia. This intervention also restored the microglia's capacity to clear amyloid plaques and improved markers of neuronal health in animal models of Alzheimer's disease. This suggests the potential for an entirely new therapeutic strategy, one that does not target the amyloid plaques themselves, but rather addresses the underlying lipid metabolism that impairs the brain's defense mechanisms. This opens avenues that pharmaceutical companies have not yet actively explored, bridging Alzheimer's research with lipid biology, metabolic diseases, and the significant portion of the population living with obesity. Consider the far-reaching implications. Alzheimer's disease has been the subject of intensive research for decades, primarily viewed as a problem involving protein misfolding, the accumulation of amyloid and tau tangles, and neuroinflammation. Numerous drugs have been developed with the aim of removing plaques or preventing their formation, yet most have ultimately failed. What if the reason for these failures lies in the fact that they were addressing symptoms rather than the root cause? What if the true driver of the disease is subtly hidden in plain sight, residing within the fat that permeates our cells and transmits signals we were previously unaware of? Chapter 5. The Domain That Primed the World. Long before the emergence of dense forests, before the proliferation of grasses, and prior to the first moss taking root on the damp rocks at the ocean's edge, a different entity was already present, not in a state of passive waiting, but actively engaged in work. It was engaged in the painstaking process of breaking down stone, facilitating nutrient cycling, and constructing the fundamental chemical framework that would ultimately enable all subsequent life forms to flourish. Our common perception of terrestrial life often begins with plants, the green pioneers that colonized a previously barren surface. However, this surface was not entirely devoid of activity when the plants arrived. It had been meticulously prepared over hundreds of millions of years by a kingdom that largely escapes our notice, the fungi. On the first day of October, 2025, researchers affiliated with the Okinawa Institute of Science and Technology published a significant study in Nature Ecology and Evolution. This paper fundamentally revises the established timeline of terrestrial life by employing a novel combination of fossil evidence and an innovative technique involving horizontal gene transfer. Horizontal gene transfer refers to the phenomenon where genes jump laterally between species, rather than being passed down vertically from parent to offspring. Through this approach, they traced the evolutionary origins of fungi back much further than previously anticipated. The common ancestor of all currently living fungi is estimated to have existed between 1.4 billion and 900 million years ago. To provide context, land plants appeared on Earth approximately 470 million years ago. This indicates that fungi had been undergoing diversification for potentially a full billion years before the first plant managed to establish a foothold on land. This is not a minor adjustment to existing theories. It represents a profound alteration of the entire narrative of life's evolution. Complex multicellular life, comprising organisms made of numerous cells with specialized functions, evolved independently on Earth precisely 5 times. Animals, land plants, fungi, red algae, and brown algae. Each of these groups developed its own unique mechanisms for cellular adhesion, communication, and organizational structures to form tissues. For the majority of these lineages, fossil records provide clear chronological markers. Animals, for instance, appear in the geological record around 600 million years ago, evidenced by formations like the Ediacaran biota with their distinctive imprints. Red algae, possibly as early as 1.6 billion years ago, are found in ancient fossilized seaweed-like structures from India. However, fungi leave behind remarkably few fossils. Their biological structures are soft, thread-like, and prone to rapid decay, making their evolutionary history a puzzle with many missing pieces. The research team, led by scientist Gergely Salisi, utilized horizontal gene transfers as crucial temporal indicators. When a gene from one fungal lineage successfully jumps into another, it establishes a fundamental rule. The ancestral lineage of the gene donor must be older than the recipient lineage. By identifying 17 such instances of gene transfer and integrating this information with the limited fossil evidence, the team was able to constrain the fungal evolutionary timeline with an unprecedented degree of accuracy. The picture that emerged depicts a kingdom that dominated Earth's continents for an almost incomprehensible span of time. Consider the implications of this finding. For hundreds of millions of years, potentially approaching a billion years, fungi constituted the most complex life forms on land. They were not entirely alone. Algae existed in the oceans and likely in shallow coastal environments, and bacteria formed extensive microbial mats. However, fungi possessed distinct capabilities. They were actively engaged in complex chemical processes that no other life forms of that era could perform. They release secretions that disintegrate rock, freeing phosphorus and other essential elements trapped within minerals. These organisms construct intricate networks, forming delicate filaments that link disparate soil areas, effectively transporting vital resources across entire landscapes. They also forge alliances with other living beings, engaging in mutually beneficial exchanges where they provide nutrients and receive sugars, establishing symbiotic relationships that advantage all parties involved. Researchers uncovered evidence indicating that certain ancient fungi possessed the capability to degrade pectin, a key component of plant cell walls, as far back as 1.2 billion to 800 million years ago. This discovery implies they were in contact with algae, potentially aiding their survival in the challenging transitional zone between aquatic and terrestrial environments. By the time plants eventually developed and began colonizing continents, they did not encounter an untouched world. Instead, they found a terrestrial realm already shaped by fungal activity, characterized by rudimentary soils with established nutrient cycles and functioning chemical pathways. This revelation challenges the conventional narrative of pioneers. Plants did not conquer land through their own solitary efforts. They inherited a world meticulously prepared by fungi over immense periods. Upon their arrival, plants immediately established partnerships with fungi. These associations are now recognized as mycorrhizae and are ubiquitous. 90% of contemporary land plants host fungal partners, either within or adjacent to their root systems, engaging in a sugar-for-mineral trade. It is highly probable, indeed almost certain, that plants would have been unable to colonize land without these partnerships. Furthermore, these crucial alliances likely trace their origins, both literally and evolutionarily, back to the initial interactions between fungi and algae in the primordial waters. Chapter 6. The Deceptive Vinegar. In March of 2024, a modest clinical investigation was disseminated in the periodical BMJ Nutrition Prevention and Health. This research, originating from Lebanon and spearheaded by investigators at the Holy Spirit University of Kaslik, involved 120 young individuals with an average age of 17, all classified as overweight or obese. The participants were systematically divided into 4 distinct cohorts. 3 of these groups were instructed to consume apple cider vinegar each morning in quantities of 5, 10, or 15 milliliters, diluted in water and taken prior to meals. The 4th cohort received a placebo, a synthetic vinegar that mimicked the appearance and taste of the genuine article, but lacked the active compound, acetic acid. The trial spanned a duration of 12 weeks. The outcomes, as detailed in the published manuscript, were astonishing. Individuals who consumed the vinegar experienced weight loss, not insubstantial, averaging between 6 and 8 kilograms, with the most significant reductions observed in those ingesting the highest dosage. Their body mass index decreased, and measurements of their waist and hip circumferences diminished. Moreover, their blood glucose levels, triglyceride counts, and cholesterol profiles all showed marked improvement. The paper posited that apple cider vinegar decelerated gastric emptying, thereby fostering a sense of satiety and diminishing appetite. It presented graphical representations and statistical analyses that clearly demonstrated considerable disparities between the vinegar-consuming groups and the placebo group. The journal, in conjunction with a press release, published this study. Media organizations globally seized upon the findings. Headlines trumpeted a straightforward and economical remedy for weight management. Apple cider vinegar, a staple in many kitchens, was suddenly being hailed as a miraculous solution. The study achieved widespread recognition, proliferating across articles and social media platforms. Influencers began advocating for daily consumption of vinegar shots. The apple cider vinegar market, already valued at over $1 billion, experienced a resurgence of interest. Individuals referenced the study in online forums, blog posts, and personal conversations, lending it credibility due to its publication in a journal affiliated with the BMJ Group, a reputable entity in medical publishing. Nevertheless, a segment of the research community harbored reservations from the outset. A professional named James Heathers, a consultant specializing in research integrity, commenced an examination of the paper shortly after its release. His findings proved disquieting. The age and body mass index distributions across the 4 experimental groups exhibited an improbable degree of similarity. Statistically speaking, this level of uniformity is highly unusual. When subjects are randomly assigned to groups, some variability is anticipated. However, the groups in this particular study appeared almost perfectly matched, suggesting deliberate balancing rather than random allocation. Heathers subsequently published an analysis in May of 2024, detailing what he termed implausible data patterns. He highlighted that, if the reported results were accurate, apple cider vinegar would demonstrate 50% greater efficacy than prescription medications such as Ozempic, which carry substantial costs and require medical supervision. The notion that a mere tablespoon of vinegar could yield superior outcomes compared to cutting-edge pharmaceutical interventions stretched credulity. Additional researchers voiced their concerns through correspondence to the journal. The study had not been pre-registered, a mandatory procedure under the BMJ Group's editorial policies, designed to prevent the selective reporting of findings. The statistical methodologies employed were ambiguous. Attempts to independently reproduce the analyses using the published data proved unsuccessful. The BMJ Group's content integrity team initiated a formal inquiry. They forwarded the paper to independent statisticians, tasking them with assessing its dependability and attempting to replicate its results. These statisticians were unable to do so. They identified numerous analytical inaccuracies. Furthermore, they detected anomalies within the dataset that indicated a need for independent scrutiny of the underlying raw data. The numerical totals did not reconcile. On September 23, 2025, 18 months after its initial publication, the journal officially retracted the paper. The retraction notice was direct and unequivocal. The findings were unreliable, multiple errors had been identified, and the data could not be validated. The authors, in their response, attributed the errors to honest mistakes and concurred with the decision to retract. However, the impact had already been substantial. For a period of 18 months, the study had been frequently cited as definitive evidence. It was incorporated into systematic reviews and meta-analyses, which synthesize findings from numerous studies to derive broader conclusions. One such review, published shortly before the retraction, partially relied on this flawed data to suggest that apple cider vinegar might contribute to weight management. This review is now compromised, built upon a foundation that includes either fabricated or profoundly erroneous results. An editor at the BMJ Group, a Ms. Helen MacDonald, issued a public statement. While acknowledging the temptation to alert readers to what appeared to be a simple and beneficial aid for weight loss, she asserted that, at present, the results of the study are unreliable, and journalists and others should no longer reference or use the results of this study in any future reporting. However, the question remains: how many articles persist online, uncorrected, still referencing this retracted research? How many individuals altered their behavior based on information that ultimately proved to be untrue? Chapter 7. The Moon's Divided Heart. Our moon possesses 2 distinct faces, and they are not alike. This difference is readily observable even with a basic telescope. The near side, the hemisphere perpetually facing Earth, is characterized by numerous dark regions known as Maria. These are ancient plains of solidified lava that filled impact basins billions of years ago. The far side, concealed from our direct view until spacecraft ventured beyond its orbit, presents an entirely different appearance. It exhibits fewer maria and a greater abundance of craters, suggesting a landscape that appears older and has undergone less modification from volcanic activity. For decades, this pronounced asymmetry has perplexed planetary scientists. The fundamental question is why one hemisphere of the moon should differ so dramatically from the other, given they are integral parts of the same celestial body, formed from the same material, and subjected to the same cosmic history. Or, at least, so it was believed. On October 3, 2025, researchers published an analysis of lunar samples retrieved from the far side by China's Chang'e 6 mission. These samples represent the inaugural specimens collected from that particular hemisphere and offer insights that challenge our prior understanding of the moon's internal composition. The rocks are exceptionally rich in minerals, typically formed from magma, which is molten rock that is cooled and solidified. However, their chemical makeup deviates from expectations. The samples contain a lower concentration of heat-generating elements, specifically fewer radioactive isotopes of potassium, thorium, and uranium, compared to rocks originating from the near side. This observation is significant because these elements are crucial for maintaining a planetary interior's warmth. Their decay over vast geological timescales releases energy that can drive volcanic processes, melting rock, and facilitating its ascent to the surface. The researchers concluded that the far side originated from cooler magma, not just marginally cooler, but substantially so. This finding implies that the moon's interior is not uniform. It is not a simple, symmetrically layered sphere comprising a crust, mantle, and core. An inherent asymmetry exists within its deep structure, with compositional and thermal differences between the near and far sides dating back to the moon's initial formation. The prevailing theory regarding the moon's genesis involves a colossal impact event. Early in Earth's history, approximately 4.5 billion years ago, an object roughly the size of Mars collided with our planet. The impact's sheer violence vaporized rock, creating a disk of debris that orbited Earth. This debris gradually coalesced, drawn together by gravitational forces, ultimately forming the moon. However, this accretion process was neither smooth nor uniform. It is highly probable that the moon was initially in a molten state, a sphere of magma slowly cooling over millions of years. As it cooled, denser minerals gravitated downwards, while lighter minerals floated to the top, establishing distinct layers. The recent findings suggest that this differentiation process occurred unequally across the two hemispheres. It is plausible that the near side, facing Earth, received additional heat from tidal forces exerted by our significantly larger planet, causing its interior to flex and warm. Alternatively, the distribution of radioactive elements may have been inherently uneven from the outset, concentrated more heavily on one side. Regardless of the precise cause, the outcome is a moon possessing a divided internal structure. This revelation holds significance beyond lunar geology, offering insights into the formation and evolution of rocky celestial bodies. We tend to assume symmetry, modeling planets and moons as spherical entities with uniform internal layers. However, if the moon, a relatively small and less complex body compared to a planet, can exhibit such profound internal asymmetry, what implications does this hold for other worlds? Mars, for instance, displays hemispheres with strikingly different appearances. The northern lowlands are smooth and flat, while the southern highlands are ancient and heavily cratered. Could Mars also possess an asymmetric interior, with disparate thermal histories on each side? What about exoplanets, the thousands of worlds discovered orbiting other stars? We are unable to directly observe their interiors. Yet, if asymmetry is a common phenomenon, our current models might be fundamentally flawed. The lunar samples also yielded another crucial piece of information. They confirmed that volcanic activity on the far side ceased earlier than on the near side. With a diminished abundance of heat-generating elements, the far side lacked the thermal capacity to sustain volcanism for as long. It became geologically quiescent, while the near side continued to erupt, filling basins with lava. This disparity creates a form of geological record, a timeline etched in rock, illustrating the gradual decline of the moon's internal heat over billions of years. By studying these samples, researchers can refine models that describe planetary cooling processes or the duration required for a celestial body to solidify internally and become geologically inactive. Chapter 8. The Ice Hiding an Ocean. Saturn boasts numerous moons, yet one in particular persistently draws the attention of scientists, garners frequent headlines, and fuels speculation about the potential for life even within our own solar system. This moon is Enceladus, a relatively small world measuring approximately 500 kilometers in diameter, enveloped in ice so brilliant that it reflects nearly all incident sunlight. From a distance, it appears pristine, frozen, and inert. However, in 2005, the Cassini spacecraft passed close enough to reveal a startling reality. Enceladus is far from dormant. It is actively erupting. From fissures near its south pole, immense plumes of water vapor and ice particles are propelled into space. These geysers ascend hundreds of kilometers above the surface. These are not isolated incidents. They are continuous and constant, sustained by a phenomenon occurring beneath the icy shell, an ocean, a global body of liquid water tens of kilometers deep, situated beneath an ice layer estimated to be between 20 and 30 kilometers thick. This subterranean ocean is kept liquid by tidal heating, a process analogous to the gravitational flexing that renders Jupiter's moon, Io, volcanically active. Saturn's gravitational pull alternately squeezes and stretches Enceladus as it orbits, generating friction within the moon's interior, which produces heat, melting the ice that, under normal circumstances, would remain frozen solid. Cassini traversed these plumes, analyzing their composition with its onboard instruments. The discoveries were remarkable. Obvious water, of course, but also salts, indicating rock-water interactions occurring on the ocean floor. Silica particles, minuscule grains of silicon dioxide that form when hot water encounters rock at temperatures exceeding 90 degrees Celsius. Furthermore, organic molecules were detected, initially simple compounds like methane, carbon dioxide, and various carbon-containing substances, though not necessarily indicative of life. Subsequent flybys revealed more complex molecules, including propane, ethane, and acetylene. Now, according to a recent analysis of Cassini data published on October 2, 2025, even more intricate organic compounds have been identified within the ice grains themselves. Researchers re-examined data that Cassini had collected years prior, applying advanced techniques and modeling to extract information that was not apparent in the initial studies. Their findings revealed organic compounds featuring multiple carbon atoms, molecules that, on Earth, are associated with biological processes, although they can also arise from non-biological chemical reactions. The presence of these compounds does not definitively prove the existence of life, but it significantly strengthens the argument that the conditions within Enceladus's ocean are conducive to supporting life. These conditions include liquid water, a source of energy from tidal heating, organic molecules, and rocky surfaces where chemical reactions can occur. Essentially, the key ingredients we seek when searching for habitable environments. What makes Enceladus particularly tantalizing is that its ocean is not isolated. It communicates directly with space through the aforementioned plumes. Any substance dissolved in the ocean water, any molecules or even cells, if they exist, can be carried upwards through the fissures and ejected into space. This implies that we may not need to land on Enceladus, drill through kilometers of ice, and deploy instruments into a dark, inaccessible ocean. It may be sufficient to simply fly through the plumes and collect samples. In principle, we could detect signs of life without ever making physical contact with the moon's surface. NASA and other space agencies have been contemplating missions designed specifically for this purpose. These would involve spacecraft programmed to orbit Saturn, repeatedly pass through the plumes, and analyze the ejected material with instruments far more sensitive than those carried by Cassini. However, a significant obstacle exists. Similar to the challenges associated with returning samples from Mars, these proposed missions undergo extensive study, design, and planning, only to face delays. These delays are often attributed to budgetary constraints, competing priorities, technical complexities, and shifts in political landscapes. The earliest conceivable launch date for a dedicated Enceladus mission is projected for the mid to late 2030s, a decade or more into the future. Meanwhile, the accumulating evidence continues to mount. Each new analysis of Cassini data unveils greater complexity and further hints that Enceladus is not merely habitable, but potentially inhabited. We have a world possessing an ocean, an energy source, and organic chemistry, actively expelling its secrets into space for us to sample, and yet we are waiting. Saturn hosts other moons with subsurface oceans. Titan, its largest moon, with its dense atmosphere and methane lakes, almost certainly harbors a water ocean deep beneath its icy crust. Jupiter's moon Europa possesses an ocean that may contain twice the volume of all of Earth's oceans combined. Ganymede and Callisto are also believed to have oceans. Our solar system, it turns out, is not a parched environment. It is a water-rich system, filled with concealed seas locked beneath ice. These oceans, present for billions of years, remain stable, shielded from radiation, and potentially teem with life forms we have yet to comprehend. Chapter 9. The Hunter Before Blood. When one contemplates a leech, the typical image conjured is that of an unpleasant creature, a dark, slug-like organism that attaches itself to skin, subsists on blood, and leaves a wound that continues to bleed due to anticoagulants present in its saliva. Leeches are, by nature, parasites, organisms that thrive by exploiting others. They possess soft bodies, making them difficult to appreciate, and are generally absent from the fossil record, as soft tissues rarely preserve. However, on October 2, 2025, researchers announced the discovery of a leech fossil that fundamentally alters our understanding of these creatures. This fossil is dated to 430 million years ago, pushing the evolutionary origin of leeches back by 200 million years earlier than any prior evidence suggested. The fossil originates from a geological formation known for its exceptional preservation, capturing not merely the external form of the animal, but also the intricate structure of its body segments, the configuration of its head, and even indications of its internal anatomy. What astonishes paleontologists is not solely the age of the specimen, but what it reveals about the nature of leeches prior to their evolution into parasitic forms. This ancient leech was not a blood feeder. Instead, it was a predator, an active hunter equipped with jaws and a body designed for propulsion in open water. It inhabited the marine environment, unlike the freshwater ponds or terrestrial habitats where modern leeches are found. In essence, it was a fundamentally different kind of animal from the leeches we recognize today. Modern leeches belong to the clade Hirudinida, within the larger phylum Annelida, commonly known as segmented worms. They are closely related to earthworms and marine bristleworms, all sharing a body plan composed of repeating segments. However, leeches have lost the bristles, as well as the rigid setae that other annelids utilize for locomotion. Instead, they have evolved specialized suckers, one situated at each extremity of their bodies, coupled with a muscular, flexible form that enables them to progress along surfaces or propel themselves through the water with undulating movements. Most significantly, many leeches have developed specialized oral structures for piercing skin and feeding on blood. This lifestyle necessitates biochemical adaptations, including enzymes to prevent coagulation and chemical compounds to evade detection, all incorporated into their saliva, transforming a simple bite into a sophisticated parasitic strategy. Yet, 430 million years ago, none of these specialized traits had yet emerged. The fossilized leech exhibited a different physique. It was longer, more streamlined, built for speed rather than for attachment. Its jaws were sharp but not adapted for piercing skin. Rather, they were designed for grasping, for securing prey, and for dismembering small invertebrates within the water column. This was a carnivore, an oceanic predator that actively swam and hunted other organisms. The researchers who studied the fossil, publishing their findings in a peer-reviewed journal, described it as a portal into a lost world, a time when leeches were not the despised parasites we know, but rather legitimate hunters within marine ecosystems. This discovery compels a re-evaluation of leech evolution. The parasitic lifestyle and blood-feeding behavior emerged at a later stage. It was not the ancestral condition. Somewhere within the intervening millions of years, a particular lineage of hunting leeches shifted its predatory strategy. Perhaps they began scavenging on carrion or feeding on the wounds of other animals. Alternatively, they might have transitioned to opportunistically feeding on live animals, extracting small quantities of blood when the occasion arose. Over time, these opportunistic feeders evolved into specialists, refining their mouthparts, saliva, and behaviors until they became the obligate parasites observed today. However, the fossil unequivocally demonstrates that leeches originated as something entirely different. This raises an intriguing question. Do hunting leeches still exist today? Are there undiscovered lineages that never underwent the transition to parasitism? The ocean is vast and largely unexplored. We possess more detailed maps of the surface of Mars than of the deep sea floor. New species are discovered with remarkable regularity, including peculiar worms and bizarre invertebrates that defy existing classifications. It is entirely plausible that somewhere within the abyssal depths, in a trench or canyon we have yet to explore, exist leeches that continue to hunt, living as their ancestors did 430 million years ago. The fossil serves as a potent reminder that evolution is not a linear progression, nor a march towards inherent complexity or improvement. It is a branching tree, with lineages diverging, experimenting, some achieving success, while others face extinction. Each adapts to its specific environment and the opportunities it presents. Chapter 10. How Words Rewrite Reality. There exists a form of manipulation so subtle, so insidious, that the recipient remains unaware of its occurrence until their grasp on reality has already begun to loosen. This phenomenon is known as gaslighting. This term originates from a dramatic work penned in 1938, which later saw adaptation into a motion picture. The narrative centers on a husband who systematically distorts his wife's perception of reality, causing her to doubt her senses, her recollections, and her very mental stability. He would subtly dim the illumination in their dwelling, and then adamantly assert that no alteration had occurred. He would conceal personal effects, and then accuse her of misplacing them. His constant refutation of her accounts eroded her self-assurance. While the original play presented a fictional scenario, the psychological phenomenon it portrayed is a deeply disturbing reality. On the 2nd day of October, 2025, scholars affiliated with McGill University and the University of Toronto unveiled research that recharacterizes this deceptive tactic, not as mere falsehood, but as a learning procedure intricately linked to how our brains process incongruent data. The study, disseminated within a scholarly publication focused on neuroscience, elucidates gaslighting as a corrupted form of associative learning, wherein persistent exposure to fabricated information from a trusted individual can supersede direct sensory input. They elaborate that your cognitive apparatus is perpetually engaged in constructing a conceptual framework of the world, a mental schema designed to anticipate future events. This internal model is continuously refined by two distinct information channels: what you directly apprehend through your sensory faculties and what you acquire from others, particularly those you hold in high regard. Under typical conditions, these two streams harmonize. You observe a crimson piece of fruit, and someone informs you it is indeed red. This corroboration fortifies your mental model. However, gaslighting introduces a discord. You perceive a red fruit, but an individual you trust declares it is green. Your brain is now confronted with a quandary. Which information source warrants greater credence? If the individual contradicting you is someone upon whom you rely, someone whose past pronouncements have proven accurate, or someone who wields social or emotional influence over you, your brain might elect to give their assertion precedence over your own visual evidence. This is not a conscious or deliberate choice, but rather an automatic recalibration of the cognitive learning mechanism your brain employs to navigate its environment. The researchers employed neuroimaging and experimental observation to investigate this phenomenon. They presented participants with a sequence of visual stimuli, followed by pronouncements from confederates, individuals collaborating with the experimenters, who provided inaccurate descriptions of the images. These confederates were presented as authorities, individuals possessing specialized knowledge, thereby establishing a context where their pronouncements carried significant weight. Across multiple repetitions, the participants began to question their own perceptions. When subsequently asked to recall the visual content, they increasingly recounted the fabricated information provided by the confederates, rather than what they had genuinely witnessed. Brain scans revealed heightened activity in neural areas associated with conflict resolution and memory reconsolidation, regions that activate when the brain reconfigures existing information to integrate new data. This is not indicative of deficiency in intellect or character. Rather, it represents the brain functioning as it was evolutionarily designed, to learn from communal knowledge. Humans are inherently social beings. Our survival depends on the exchange of information and reliance on the collective wisdom of our communities. If every member of your group warns you that a particular plant is noxious, you are not compelled to ingest it yourself to confirm. You trust their collective knowledge, and that trust is a vital component of your preservation. Nevertheless, this same system, this mechanism of social learning, can be exploited. When an individual in a position of authority consistently disputes your lived experience, your brain may begin to prioritize their interpretation of events over your own personal recollections. You commence to doubt your judgment. You scrutinize your own perceptions. You experience confusion, disorientation and a sense of detachment from tangible reality. In essence, you are, as your internal model of the world is being reshaped by the assertions of another. The ramifications of this are far-reaching. Gaslighting transcends mere abstract psychological maltreatment. It constitutes a direct tampering with neural processes, an exploitation of the very ways in which the brain acquires knowledge and forms memories. The researchers strongly advocate that comprehending this operational principle is the initial stride toward developing defenses against it. If you recognize that your cognitive framework is susceptible to authoritative refutations, you can implement protective measures. You can maintain documentation, meticulously record events, capture visual evidence through photography, and establish external reference points for your memory that cannot be expunged by another's persistent denial. You can also seek corroboration from a diverse array of individuals, cross-referencing your perceptions with those outside of the relationship characterized by manipulation.